Welcome, everyone, and good morning, or good afternoon, or good evening, depending on where in the world you are. People from over 70 countries have registered for this event. My name is Arvind Narayanan. I'm a professor of computer science, and I'm also part of the Princeton Language and Intelligence Initiative. So it's great to see so many of you here. Between Zoom and YouTube, we have over 200 people already, and I'm sure many more are going to be coming in. So it's clear that this workshop has touched a nerve. I think building useful and reliable AI agents is something that so many of us want to learn how to do. I think there are two reasons for that. One is the shift from deploying models to building and deploying compound AI systems, which are often called agents or agentic systems. I won't give a definition of an AI agent right now, but we'll hear about it later in the day. But roughly speaking, it might look something like what's shown on the slide. The details aren't too important. But the point is that there is so much interest in agents from all quarters in the product world, in industry research labs, in academic research. Now, if you're someone who doesn't think companies will be able to scale up large language models all the way to AGI, then surely what we're going to see more and more is that models themselves are not deployed directly, but will be one component of a larger AI system. That's probably what AI is going to look like in the future. And of course, what people naively think of as models like ChatGPT or Claude are actually agents. They have input and output filters. They are able to use tools through code execution. They're able to do retrieval augmented generation, both through web access and by connecting it to your documents. And they can do chain of thought reasoning. So, in a way, agents are already widely used and successful. So that's the first reason why I think today's workshop is timely. The second reason is that on the flip side, when it comes to more ambitious visions of what agents can do, there is still a big gap between hype and reality. So on the left here is the vision from the movie Her, which you're probably familiar with. And on the right is an example of a product that tried to do ambitious things with a mainly voice-based user interface. There was a famous negative review of it from Marcus Brownlee. And here's another one. You can see here in this example that it delivered to the wrong address. We've had these reliability problems with Siri and Alexa for a long time, but it's one thing when your voice assistant plays the wrong song 10% of the time, and it's a very different thing when your food gets delivered to the wrong address 10% of the time. One is annoying, and the other is a product that's, kind of dead on arrival. I point this out not to criticize these products. Anyone who's tried to build agents knows what a hard problem it is, especially in consumer-facing products. Now, of course, there are many other uses of agents that are not consumer facing. We've even heard of automating the design of agents themselves in a recent research project, for instance. So there are many challenges. I think one is infrastructure. This is a new way to build software. So we need developer tools. Fortunately, there are already many developer tools, and we're going to hear from the creators of some of the most important ones today. The second is cost. It's still cost prohibitive for agents to do things like constantly monitor what a user is doing and offer assistance. So we need to think carefully about trading off between cost and usefulness. A third difficulty is reliability, which we've already talked about a little bit. How do you build software that behaves predictably and deterministically when you're working with LLMs that are fundamentally stochastic components? I think that's still an unsolved problem. And of course, we have to solve privacy, safety, and security. And we're glad to have a speaker from the UK AI Safety Institute today. And finally, in consumer applications, there's a user interface. Knowing when to escalate to the user is a very tricky problem, especially in assistance with voice-based interfaces, which are very constrained interfaces. Now, in traditional machine learning, you could look at the benchmark performance of a model. and you at least have a rough sense of how the model will perform in production. But with large language models, the gap between benchmarks and sort of vibes started to increase. And with agents, it's an even harder problem. That's what we found in our paper called AI Agents That Matter, which you can see on the slide here. I don't mean for you to read all this. And by the way, I see in the chat that some folks are saying they can't see the slides, but I think a lot of others are saying they can see them. I apologize from my end. It looks like I am sharing slides, but maybe there's something you can fiddle with in your Zoom if it's not working for you. Sorry about the technical difficulties. So we're going to hear about this paper from Sayash and Benedict. And our findings in this paper were a big part of our motivation for organizing this workshop. So we think there is an urgent need to improve evaluation methods, and we're going to have a whole session on that. So with that, these are the primary organizers. I'm going to turn it over to Sayash and Benedict in a minute, and Nithya and Zach will give closing remarks. All four of them did a huge amount of work to make this happen. And I should also thank Ellen DePippo, Chris Lambert, and Neil Betwin for administrative support. Having said that, welcome again. This is going to be an exciting 4 hours of talks and discussion. Thank you.
All right. Hello, everyone. I'm Sayash Kapoor. I'm a CS PhD candidate at Princeton. And I want to talk a little bit about why we organized this workshop. But before we do that, some quick housekeeping. So today's workshop will have 3 main sessions. Each session will be an hour long. And each session will have 30 minutes of talks, followed by 30 minutes of Q&A. What this also means is that please feel free to put in your questions on the Zoom chat, or if you're following along on the YouTube live stream chat, and we'll make sure to pass them on to the moderators. We'll have a 15-minute break between each of the sessions. Now, as Arvind mentioned, there are a number of reasons why building useful and reliable AI agents is hard. And the reason we're organizing this workshop is mostly based on the findings of a recent paper. The paper is called AI Agents That Matter, and it tries to answer how we can make agents that are useful in the real world and not just on benchmarks. Our first surprising finding is that one-dimensional agent leaderboards can be somewhat misleading. Now, that can be a strong claim because for the longest time, we've relied on leaderboards that measure accuracy. And so long as you're sort of increasing accuracy on the state-of-the-art leaderboards, you're basically good. So why is that different for AI agents? One key insight is that when it comes to agent, maximizing accuracy without any constraints can lead to an unbounded cost. In particular, for many agents, we are seeing that as you scale the inference compute, the accuracy keeps on getting higher. And so reaching the state of the art on an agent benchmark could just be about calling the underlying language model multiple times. In domains where we have some form of verification, this trend can hold for up to millions of calls. So for example, many coding benchmarks come with test cases to check if the given code or the code outputted by an LLM is correct. What happens if we keep retrying these benchmarks until we solve the visible test cases with any test set? So the original AlphaCode paper by Lee et al. Showed that the pass at 10 accuracy continues to increase with an increase in the budget for up to millions of model calls. We've also seen similar results more recently. Snell et al. Showed in a paper released just this month that pass at 1 also keeps increasing for the math benchmark, and Brown et al. Showed that you can keep increasing accuracy on SweBench Lite as you increase the number of attempts. And I think the third paper will be discussed by Azalea in the third session today. So in order to view performance as multidimensional rather than just one-dimensional, we plotted the Pareto frontiers of accuracy and cost. So instead of agent leaderboards topping these, or agents topping these agent leaderboards, you have a Pareto frontier that defines what the best agents are along a curve. So it gives you a set of trade-offs to choose from. Do you want to use an agent that's more expensive, but perhaps better performing? Or do you want a more inexpensive, but slightly worse one? So we think that Pareto frontiers will be the future of agent evaluation. And in order to instantiate such an experiment, we asked a very simple question. What is the best agent performance on human eval, the popular coding benchmark, in terms of accuracy as well as cost, if we account for cost as well using Pareto curves. So we tried to reproduce the top 3 agents that had publicly available code, and we evaluated not just the accuracy, but also the cost. In addition to these state-of-the-art agents, we also evaluated very simple baselines. Things like retrying a model multiple times if it fails the given test sets. And what we found was that basically all of these simple baselines were good enough to perform about as well as state-of-the-art models. So in particular, here's the Pareto frontier. You can see the LDB agent performs about the best. This was not surprising. But what was surprising for us was that just increasing the temperature as we retry the model multiple times, what we call the warming agent, did about as well as LDB, but at less than half the cost. And it was also interesting to see that increasing the temperature over multiple retries did increase performance compared to simply retrying the model multiple times. Now, what both of these things tell us is that Pareto curves are necessary for seeing these improvements. If we did not use this type of analysis, we wouldn't really be able to tell if we are actually improving over the state of the art or if we are just mapping its accuracy. More importantly, while as academics, we might care more about having the top leaderboard performance, especially in the field of ML, downstream users absolutely care about cost. Spending twice the cost for running an agent that does just 0.1% better might be absurd from the perspective of a downstream user. And that's why it's crucial when developing complex agent architectures to also use strong baselines, such as just retrying a model multiple times or improving or increasing the temperature as you retry to basically answer the question of whether it even makes sense to explore these complex models in the first place. Now, once we start looking at agent leaderboard performance as 2-dimensional instead of just 1-dimensional, this also opens up a completely new design space for designing agent benchmarks. And more importantly, for designing agents that optimize both accuracy and cost. In particular, once we start looking at all of the design choices that an agent makes, we find that agent developers might use shorter prompts, they might use better few-shot examples, they might use cheaper models that can be optimized or fine-tuned to do about as well as larger ones. And finally, they might use techniques like prompt caching. And this basically opens up an entirely new set of design choices to optimize around, which we feel has not been paid attention to, especially in academic research on agents. And as a result, the agent designs that we sort of end up with might be unnecessarily expensive. So once again, we tried to test this hypothesis, and we tested it using the DSPy framework. We'll hear from the developer of DSPy, Omar Khattab, in the first session. But we looked at DSPy, and we tried to modify the framework to jointly optimize accuracy as well as cost, instead of just optimizing for accuracy. And what we found was that by jointly optimizing accuracy and cost, we could basically reduce the cost to about half without giving up much in terms of accuracy. So in this figure on the top right, we have the default DSPy optimizers, the few-shot and random search optimizers. And on the middle here, we have our joint optimizer. Now, to be clear, the joint optimizer is not doing anything sophisticated. This is really just the simplest possible implementation. On a small dev set, you can try multiple prompts, try decreasing the size of these prompts, try decreasing the size of the few-shot examples, and then just pick one that works best. We are certain that we can do a lot better than that. But what we're trying to show with this example is that this huge design space between running the models zero-shot or few-shot and running optimized versions of models for huge gains, I think there's a large design space that exists between these two in terms of finding clever ways to optimize agents. Okay, I'll have one more sort of remark to offer on cost optimization, and then I'll switch it over to Benedict. So one response to all of this work on cost optimization for LLMs might be that LLMs are becoming too cheap to meter, and soon we wouldn't need to care about cost at all. There is indeed some truth to this statement. The cost of running models has reduced drastically. So if we look back at OpenAI models a couple of years ago, if you ran Text DaVinci 003 compared to GPT-4o Mini, I think the cost has reduced by 2 orders of magnitude, and performance has actually improved. But the fact remains that running these language models is still extremely expensive, especially for applications that need to scale, sometimes to hundreds of thousands, or perhaps even millions or billions of users. Moreover, this cost is still a major barrier for research. So for context, just for running the experiments in the paper we're talking about, we spent around $10,000 in compute costs alone. And this also has implications for evaluating the safety. So especially for benchmarks like SciBench from Stanford, which evaluate the cybersecurity capabilities of a model, you could imagine cost being an important factor in determining whether a low resource adversary, such as a script kiddie, can carry out an attack, or only high resource adversaries like state-sponsored attackers can carry out attacks. And finally, even if the cost of running an individual LLM call might be really, really low for many applications, even in the short to medium term, we think that the total cost of running LLMs for any given industry or domain might still be very high. And the way to illustrate this that I found most helpful is this theory from economics known as the Jevons paradox. So Jevons was this 19th century economist who observed that as we improved our technical capacities for efficiency of coal use, we actually started using more coal and not less. And we've seen this play out in many other domains as well. One of my favorite examples is in automation. So when we started using automated teller machines or ATMs, we basically saw that this increased the number of bank branches because suddenly it was much cheaper to create a new branch, and it also increased employment for bank tellers. Now, I think a similar trend could hold for AI models as well. In particular, as these models get cheaper, especially because of scaling for inference and improving inference, we might start calling the same model multiple times in order to solve any specific task. And we might also start using AI for more applications. So all of this means that we still think cost optimization is useful. We also still think that simple baselines like retrying models multiple times can be extremely important in order to see how well an agent architecture is really doing. All right, and now I'll hand it over to Benedict, who'll share how we see the future of agent benchmarks evolving.
Thank you, Sayash. Great. So why do we even care about making agent evaluations more useful for downstream users and in general more valid? I mean, one could argue that leaderboards actually are mainly used for tracking scientific progress, and members of the research community might be well aware of some of the shortcomings that Sayash has just talked about of current agent evaluations, and with that are equipped to interpret the results they see or read accordingly. However, we think this is not quite true, and there are actually already examples of where agent benchmarks are a crucial source of information to make consequential decisions in this fast-growing field of AI agents. So one example I just want to mention here from a couple months ago is actually the startup Cognition AI that in March this year released the then state-of-the-art agent called Devin. And then in response to that, over the couple of weeks after this release, saw their valuation rise from 350 million up to 2 billion, at which they then closed a major financing round of 175 million. And this was mainly motivated and informed by the results on the SPADE benchmark. Another example from just 2 weeks ago is actually the startup Cosign that, again, on the SPADE benchmark, released a new state-of-the-art agent called Genie, which outperforms the current top-performing agent by multiple percentage points, and then secured a multi-million-dollar seed financing. However, this is great, but we are not quite there yet for many benchmarks, and still we have identified in the paper that still many recent agent benchmarks have shortcomings. And I think we can break those down into two big categories. The one is what we measure, and the second one is how we actually run those evaluations. So in terms of what we measure, I think it's great that SPADE is used for that because it's a really good example of how a useful benchmark can look like and how a benchmark that is realistic can actually inform meaningful downstream decisions. However, for many other benchmarks, we have actually found that they still lack realism. And the crucial issue here is construct validity. And what I mean by that is similar to, as Arvid explained, is that if a benchmark developer selects tasks that are not quite that realistic, then an agent that performs very well on this benchmark might not translate at all into real-world ease of use and usability. So you can imagine a web agent benchmark that is framed around two particular categories of websites, such as online forums or online shopping, but is then interpreted in the real world as measuring general web capabilities. So then if an agent performs well on this benchmark, it might dramatically fail. So if then confronted with this more open-ended kind of web tasks. And then the second point for where many recent benchmarks still have shortcomings is actually in how we evaluate on them. And here in our paper, AI Instead Matter, we identified that many benchmarks don't have a held out set and don't provide a specific set of tasks that is only used during the final evaluation, during the final testing. And we think that this actually provides the risk to agent developers to write prompts that are too specific to the training data. And this, for example, could look like providing a specific set of policies that outlines a set of instructions that the agent needs to follow when confronted with a certain task that is part of the train set, but that is not able to handle kind of new unseen tasks in the production environment for which none of the existing policies might apply, again, leading to a potential drop in performance. And then the second more general issue of lack of standardization and reproducibility. So in our analysis of the Babarina benchmark, a very popular benchmark to measure web capabilities, as well as Human Eval, the programming benchmark we've already talked about, we found that many top agents on these benchmarks are actually not reproducible, and we had to spend even days to just get them to run. The issues we identified were, for example, that some of these evaluations across agents were run on different subsets of the benchmarks, so certain tasks were left out because they didn't apply to that specific setting, or that baselines were underreported, and even some evaluation codes developed had bugs in them and just lead to erroneous results. And to be clear, we are not blaming these on the agent developers, but we think that this is kind of an issue of the general agent evaluation ecosystem and must be addressed as such. So the good thing is that frameworks such as Helm and OpenLLM Leaderboard that many of you might be familiar with have actually successfully addressed similar concerns for language model evaluations. And here the solution was that in order to overcome these issues, we need to provide a centralized and standardized one-stop shop for model evaluations. And what I mean by that is that on these platforms, models are evaluated on a series of scenarios and benchmarks, and all are evaluated with the same kind of underlying harness, so the same code for running those evaluations. And they provide also full transparency into those by open sourcing not only the code, but also every single model call with the exact input and output that was produced during those evaluations. The caveat with that, though, and that's maybe unfortunate, is that agent evaluations differ quite significantly from model evaluations, and that's why we can't just use those existing efforts and integrate agent benchmarks and agent evaluations on them. And this is mainly because while model evaluations usually consists of an input and output of text strings, for agent evaluations, we also have most of the time an environment that the agent needs to interact with, such as a web browser environment, for example. And we have a set of tools that the agent uses over multiple rounds of interactions. And this fact that an agent can call a model, an underlying language model, multiple times and have multiple rounds of interactions actually directly leads also to this issue of unbounded cost that Sayash has already talked about quite a bit. And lastly, while it is true that for model evaluations, we can usually use the same foundation model and evaluate it across a series of scenarios and benchmarks, this is not true for most agents because they're designed to be task specific, to be good at solving one particular task, such as online shopping or travel planning. So this matrix of agents and tasks is actually very sparsely populated, and we think that it's crucial to address this in designing a similar platform for agent evaluations that is different from Helm or the OpenLLM Leaderboard. So this is actually where we want to introduce our holistic agent leaderboard that we call short HAL, which is specifically designed to address and overcome some of these shortcomings and to be a third-party, standardized, and cost-controlled one-stop shop for hosting agent evaluations. So third-party, because we want to prevent the risk for agent developers to actually have this misincentive of having to run their own evaluations while developing an agent. So just as car manufacturers, for example, do not run their own crash safety tests, we also think that agent developers should not be the only ones responsible for developing and running evaluations, but that for downstream users, it's actually more valuable to have a trusted third party that takes care of that. Standardized because each evaluation hosted on HAL is run in the exact same way with the exact same code. And cost controlled because we think that it's most meaningful for downstream users to understand the accuracy cost trade-off in order to be aware of what agent has what capability and at what cost. And in order to now give you a quick demo of the current state of HAL, what our vision with it is, and the features that we have already implemented, let me quickly switch over to a quick demo of what HAL currently looks like. So 1 second. So yes, so welcome to the current state of our holistic agent leaderboard. So first of all, who is this for? So we envision this actually to be useful for an audience that goes much beyond just the research and science community, but to be also useful for downstream users and procurers that are interested in maybe deploying an agent in their domain. Of course, for benchmark developers and agent researchers, in order to show their work, publicize it, make sure a benchmark is adopted by users, and also to connect with potential downstream developers that are using their work. And lastly, also for safety researchers, because in order to understand what are the recurring failure modes, what are the approaches that agent takes, and what are the maybe potential downstream harms that they can create, I think visibility and providing visibility into agents is a crucial feature that we will also provide with HAL. So diving in, the core piece and the centerpiece of HAL is, of course, the leaderboards. And you can already see that we have implemented a series of popular benchmarks. The one we focus on for this demo is the USA Computing Olympiad benchmark developed by Shi et al. That has a set of challenging computer programming challenges, but also the very popular SWE-bench Verified and Light, and the machine learning benchmark called ML Agent Bench. SWE-bench being developed by Jimenez et al. And ML Agent Bench was developed by Huang et al. So now, what does the leaderboard look like? This is, of course, by design, cost controlled. So while we, of course, provide specific benchmark-specific accuracy metrics, we will always also report a measure of cost that measures how costly it is to run an evaluation, along with error bars that are available for evaluations that we have run multiple times. This then allows us to actually draw a frontier of the current state of the art on a given benchmark that not only gives downstream developers the chance of evaluating the accuracy cost trade-off, but also incentivizes agent developers to get their agent on the frontier. Then next, the task success heat map. So we think that this is could be a crucial feature to understand what is the different kinds of tasks that agents might be good at solving. So whether one agent is good at solving a certain kind of task, but another agent is maybe good at another kind of task. So this could, for example, motivate combining two efforts, as well as an overall progress report of what fraction of the tasks of a benchmark were solved by any agent on the leaderboard. We talked about visibility features, and here is where the agent monitor is really the centerpiece. It consists of two components. The first one being a qualitative LLM-generated failure report that summarizes recurring failure categories of an agent and shows the fraction or the breakdown of the total number of failures on these categories per agent. And on the left, a short description of what these categories actually mean. And the second component being the task overview that allows a user to really dive in and explore individual tasks that an agent has tried to solve and understand a step-by-step description of what the approach kind of entailed and what steps the agent took. Then lastly, similar to existing efforts, we also want to provide full transparency. So we provide every single model call that was invoked by an agent during such an evaluation on any given task, logged by the weights and biases weave library, alongside not only the input and output strings, but also detailed usage information in terms of token count. So while this summarizes the current state of the HAL leaderboard, and of course, this is under development. We're adding benchmarks as we speak. But this is exactly the reason why we want to encourage you, especially downstream users and developers, to let us know what are the key pain points and the key issues you have or see with agent evaluations, in order for us to make sure that we can develop how to be as useful for you. Then for agent developers and benchmark creators, I think we really want to stress that we think that's a great idea to work towards kind of the standardized platform that has been so successful for model evaluations, also for agent evaluations, in order to connect downstream users with the work we are doing in the lab, and also for safety researchers to really think about how cost-controlled evaluations can be useful for making inferences in that field, and understand what capabilities are actually available to users in practice and at what cost. So thank you so much. We're looking forward to hearing from you, and stay tuned for an update from Hal. And with that, back to Sayash for the first panel.
All right. Thank you so much for that intro, Benedict. I've seen there are a lot of excellent comments and questions on the chat. The latest one is there a link to Hal? There isn't a link to Hal yet, but we promise to be in touch with all of you soon. There are also some questions about how we should control for cost. I'll refer you to the paper in the interest of time, because we do answer those questions in the paper. But for now, I want to move us to the first session of today's workshop, which is how do we build the infrastructure for useful and reliable AI agents. We are extremely happy that we have 3 of the leading researchers in this space. We'll put on their full bios in the chat, but I'll briefly start with our first one. So our first speaker is Omar Khattab, who's a graduating CS PhD candidate at Stanford, a research scientist at Databricks, and an incoming assistant professor at MIT starting in 2025. His work spans NLP, information retrieval, machine learning. I am a big fan of a lot of his work. Today, he's presenting one of these papers that, or one of these frameworks or tools that I've used multiple times. We talked about it in my opening remarks as well, which is DSPy. We are very excited to hear from you, Omar. Over to you.
Thanks, Sayash, and thanks for the very kind intro and for the invite. Thanks, everyone, for joining today as well. All right, so I believe you all can see my screen. So this will be a brief intro to DSPy. This is work by a large number of really amazing individuals at Stanford, at Berkeley, at CMU, and just out there in the open source community. So the context of this work is that it's never been easier to prototype really impressive demos with AI. But turning those into reliable AI systems, which is a key theme of this workshop, requires a level of control and of modularity that a language model off the shelf just doesn't offer by itself. To tackle this, one theme that sort of characterizes a lot of the work in my PhD, and a theme that sort of has been growing dramatically in the literature recently, is that we should not just simply invoke language models with complex tasks, but we should build modular software that uses language models as specialized components that play special roles in these systems. Here's a number of cool examples of this. So DynSQL is a system for text-to-SQL generation. From Google, there is RAR, which is a system for reducing hallucination in language model outputs by relying on retrieval and finding citations. And AlphaCodium is a really cool system for generating code for complex problems. And what characterizes all of these is all of these little modules or boxes that are using language models within a larger control flow to break down tasks and to solve, subcomponents of these tasks. Unfortunately, even though these diagrams are really powerful and really sort of modular, in practice, things are a lot messier than they look. And this is because language models are very sensitive to how they're instructed to solve tasks. And this becomes really, really problematic and difficult when you're trying to stitch them together into bigger pipelines or into bigger systems. Because not only are you interested now in getting the system to sort of look right or to perform a task that you can eyeball and check, you're also trying to make sure that every step along the way understands the output of the previous step and that they work well together. And so in practice, even though we want to sort of design these really nice looking diagrams and build these high level systems, something we're all guilty of and sort of a pervasive problem is our systems under the hood are implemented through very large sort of strings that sort of coerce the model or try to coerce the model in intuitive ways to perform the subtasks that we're interested in. And so we have these tens of kilobytes of files that teach a certain model how to behave within a certain pipeline. But the problem is, as models evolve, as models change, as we want to sort of tweak our designs of our systems, because these are usually very highly iterative processes, we tend to falter, and we tend to be essentially stuck with a lot of this technical debt. So the big picture is that these language model pipelines that are emerging have a lot of promising properties as modular systems, but they are in practice really messy and ad hoc, and this really reduces the potential impact that they can have and the potential utility they can have. So a question that we ask in the DSPy framework and in this line of research is that, are there ways in which we can enable more systematic machine learning for building these types of programs around language models? And sort of the theme here is that we want various ways or various tools or various abstractions and algorithms that can push us closer to programming, not prompting language models. Another way I like to ask this that may appeal to some people is, what if we can combine programming languages as a systematic way of iteratively, and incrementally building software? Natural language as a really powerful way of expressing fuzzy constraints or fuzzy behavior, sort of like as priors over what our systems should do, and reinforcement learning or learning from trial and error construed broadly as a mechanism for aligning not a language model, but aligning an entire program or an entire system with our objectives, and sort of leverage the flexibility of language models rather than sort of succumb to their sensitivity. And so the way things look in DSPy is you generally don't start by a blank slate document where you're going to write, sort of string prompts from, in natural language, which, frankly, we all do at some point or another, but they often don't really work that well. Instead, you're going to focus on designing effective programs or language model programs, and you're going to define what the overall objective that you're trying to maximize is. And so this is really a number of little principles that we want to compose together in one set of abstractions. So the first thing is we really want to emphasize composition via control flow. DSPy, as the name might suggest to you, is really just sort of a DSL on top of Python, where you are really just allowed to write Python code. You can have your loops, your exceptions, you can have if statements, you could do whatever, you could have recursion if you want. You're just really building systems. But in these systems, you're going to have invocations of functionality that is fuzzily defined, like generate query or generate answer. Now, in DSPy, we don't know your task, so we're not going to pretend that we can build these generate query or generate answers for you. Instead, you're going to declare the modules that you want, these little boxes we saw in earlier instantiations of various programs out there. And you're going to do this through declarative modules that tell us what the input should be for each of these and what the output should be, and potentially what strategy should be used at the high level to sort of implement this module or this function. So here, for example, generate query is nothing but a chain of thought. So you want the model to sort of reason before it answers, that takes in some context, so maybe some retrieved documents and a question, and then generates a search query. And it's sort of composed in this forward function here below, which might look familiar to you if you've done something like deep learning in PyTorch. Now, the sort of big idea is that this is a high-level piece of code that tells us what the system should do, but doesn't actually tell us how the model should be invoked under the hood. And so a key idea is that we want to be able to compile this code into a lower-level language, which is basically into interactions with language models that actually build up these strings that invoke the model. And so a module like this here, after successful compilation, might be sort of translated into a long prompt that instructs the model in a certain way and sort of shows the model some examples where these instructions and these examples are not things that we're hard coding, but they're essentially discovered through trial and error, where the model is generating instructions or basically exploring examples that it can generate along the way, and seeing whether or not it's able to successfully teach the system to align with whatever objectives you have, like accuracy or let's say lack of hallucination. And what we see in practice is that this can actually boost quality quite a bit with a given model. But the really nice thing is that the same program that you've written can be compiled now into very different prompts under the hood that work for different models. And so with smaller models or larger models, open or closed, you can try to basically seek to potentially maximize what you're able to deliver out of these models. What's really even cooler is that many of the optimizers actually focus on updating the weights of the language model if appropriate. And so that allows you in many cases to build really efficient systems around very small models that we can teach how to sort of conduct your program through fine-tuning. Now, what makes this possible is a set of new algorithms, or what we call DSPy optimizers, that tune the prompts and language model weights in the programs that you will write. And we don't have enough time to discuss how these work in detail, but at a high level, they sort of build an initial prompt for each module. And then they generate examples of every module by running your program end to end and trying to see which execution traces actually lead to successful or high scoring outcomes according to whatever objectives you've defined. Once we have these examples, we have a lot of options. We can either use these examples that we've generated to do automatic few-shot prompting, or we can use them to generate instructions and sort of explore a large space of instructions efficiently under the hood, or we can actually leverage them for essentially reinforcement learning under the hood and updating the weights of the language models. So, we have several papers on a lot of these. These are two of the most recent that you might want to check out online. This works pretty well in practice. So a few months ago, University of Toronto researchers participated in the Medica competition against 15 other schools. And it was really cool to see that by using DSPy and DSPy optimizers, they outperformed the next best system by around 20 points in some of these tasks. University of Maryland, a month later, ran a direct case study on a suicide detection task from industry, where they pitted sort of an expert prompt engineer who worked for 20 hours and documented very nicely his entire process against running a DSPy optimizer with a simple program. And it was very interesting to see that the DSPy prompt was able to outperform the human prompt engineer by very large margins. Now, in general, sort of people have been building many state-of-the-art systems. At Stanford, we sort of are building a lot of systems with DSPy, and people elsewhere are. So there's this really cool system path for training retrieval models through prompt optimization in DSPy, IRERA for extreme classification, and Storm for generating reports or Wikipedia articles with citations. And this is widely used in production in various places by Replit, by Haze Labs, and at JetBlue, at Databricks, at Normal Computing, and elsewhere. But what's really cool, I think, is the large open source community that is sort of have oriented itself around this new paradigm. Now, we're not done. This is just the very, very beginning. There's plenty to do in this new paradigm until sort of we've addressed and achieved all of our goals. We sort of have this nice roadmap of what we're working on in the next few months, from polishing the core functionality, building much better optimizers. Optimizers that exist now are pretty good, but there's a whole lot of room for improvement, building better benchmarks so we can assess what it is that we want to hill climb on. More tutorials and more interactive optimization with human in the loop is another priority that we have. So you can learn more about the roadmap, about the documentation, read the research papers with all the links, and learn more about the team and public use cases at dspy.ai. Thank you all very much.
Fantastic. Thank you so much, Omar. Thank you also for all the audience members who have put in their questions in the chat. We will get to these questions. We have 30 minutes set aside for Q&A, so we'll get to these questions then. For now, I want to introduce our next speaker, Harrison Chase, who is the CEO and co-founder of LangChain, a company formed around the open source Python TypeScript packages. If you've worked with agents, I'm sure you've come across the term LangChain. They're somewhat they've sort of been leading the space in many of these tools for developers. And we also see many questions in the chat about DSPy and LangChain and comparing them, and we'll get to them in the panel as well. But for now, please welcome Harrison Chase.
Thanks for having me. Excited to be here. Let me go ahead and share my screen. Awesome. So I've got some slides that I want to run through. I'll probably run through a bunch of them quickly because honestly, a lot of them overlap with a lot of the points that Omar made, and I agree with a lot of them. But going through them, I actually want to talk a lot about LangGraph today. So most people are probably more familiar with LangChain than LangGraph. LangChain is a general kind of like AI framework. LangGraph is very focused on agents. So, per the topic of today's conversation, I thought that would be fun to talk about. A little bit of background of kind of like building AI systems. We've got an LLM. LLMs are great. But oftentimes we see people using LLMs as just one step of their application, combining it with other sources of computation and data. We called these chains, back at the start, and that's where the name LangChain, language chain, kind of came from. And so a typical example of this is kind of like a RAG chain. Agents are maybe an overloaded term. I think everyone has a slightly different definition of agent. One of the definitions that I like, which is a bit more technical, is basically where it's specifically around language model agents, where a language model controls the control flow of the application. So here you can kind of see an example where the language model is deciding which step to take. It's a very simple example, but you can add in looping and make it more complex. And so that to us is kind of like the main differentiator from a technical perspective of like chains versus agents. In agents, LLMs are controlling the control flow more. Typically, agents use tool calling to execute a lot of their decision making. We've seen this emerge as a pretty popular way, supported by a lot of the big labs and models for structuring output. And you often need to get structured output to determine what to do next. React is a great paper by Shenyu from Princeton that came out 2-ish years ago. And basically oversimplifying it kind of like has this idea of using a language model to think about what to do, take that action, and then observe the result and kind of like run that in a loop until the language model decides that it's done, which is super powerful. And can allow for a lot of very flexible kind of like invocations and different paths that it can go down. Unfortunately, it also suffers from going off the rails a little bit. You don't necessarily know what it's going to do. That's part of the benefit, but that's also a drawback in some way. And this can be caused by a variety of things. So ambiguity in the underlying task, the LLM not being deterministic, the tool could be misspecified, or it could be misused and return kind of like wrong results. At the end of the day, a lot of this boils down to kind of like prompting, which Omar touched on. But prompting is very hard, and so agents often aren't super reliable. So, we incorporated React things into LangChain from the very beginning. We observed that people really liked the flexibility and the idea of them, but didn't, love the non-determinism and the fact that they went off the rails so much. And so we started thinking, how can we combine kind of like the best of both worlds? And we settled on LangGraph, which we launched about 8 months ago. So at a high level, LangGraph, as the name suggests, basically represents agents as graphs. So basically as a series of nodes and edges. The nodes and edges are nothing more than Python functions. So you actually can use it with or without LangChain. It's a graph-based kind of like orchestration system, notably not a DAG because agents are often have cycles in them. And there are a few things that we think makes LangGraph very good for building controllable agents. First is basically the fact that it's very low level and very controllable. And so you can outline exactly what the steps you want it to take are. So you can create these, if you notice, like all the diagrams I'm showing are graphs. And if you look at all the agent papers, a lot of them represent agents as graphs because that's a very intuitive and natural way to think about the work that's being done and the transitions between the different kind of like roles or responsibilities or states of the agents. The basic idea is express these control flows as graphs. And it combines this idea of kind of like a chain with the more kind of like unbounded agent. And so at a high level, you've got basically nodes, which do work, edges, which decide kind of like which nodes to go to. Tool calling is heavily used. And a big component of LangGraph as well is the shared state. So when you define a LangGraph agent, you define a state of the graph, and this graph is updated by each node and is read by each edge to decide what to do. And I'll come back to this a little bit later on. And so LangGraph somewhere in the middle. A lot of different design patterns are also enabled by this graph-like thing. So subgraphs are a pretty common architecture. Multi-agent systems are kind of like becoming more popular. And one way to think about that in the LangGraph world is that's basically using a subgraph as a node. And so we make it very easy to do that. We support parallelism kind of like out of the box. We support also MapReduce style things where you may not know the number of things that you want to parallelize, which is pretty common for LLM applications. And at a high level, it's very controllable. The second big thing that we're excited about with LangGraph is the persistence layer that it provides. So basically the way that it works is every time the agent does something, so every time it goes into a node or comes out of a node, it interacts with an underlying database to store checkpoints. So this makes it great for a few reasons. It makes it great for kind of like reliability. You can resume if there's an error, you know exactly the state you were in. It also provides a concept of memory. So here you can basically see that if you invoke an agent in 2 separate turns, this persistence naturally allows for the second turn to remember where it picked up. And so like the base example of this is a chatbot with memory, but there's more complicated examples of this as well. This enables human-in-the-loop interaction patterns, which I will talk a lot about in a second. It enables these fault-tolerant kind of like multi-agent interaction patterns because we have all these checkpoints, so we can usually resume and handle failures. That's kind of like the persistence layer. Human-in-the-loop, this is something we're super excited about. If you talk about building reliable agents today, you know, if you want an agent to go off and do a task for even like a few minutes, it's probably not reliable enough to kind of like do it entirely by itself. You're going to want some human in the loop component. This requires being able to basically stop the graph at a particular point in time or stop the agent at a particular point in time, get some human input, and then resume from there. And so in order to do that properly, you basically need to have a snapshot of the agent before it stops, get the human input, update the snapshot with that, and then resume. And so this is where the persistence layer, which I just talked about, comes in really handy. And so some specific examples of doing this: human approval for tools. If you write to a database, you might want to get explicit human approval. You can edit the state in real time. So this persistence layer, it's not just the agent that can update that. Humans can also update that. And so it's one way to think about this as well is that you've got this shared state that humans and agents are collaborating on, which enables some of this human agent collaboration pattern. Yeah, I think human in the loop, very excited by that. Another UX that we think is super important is streaming. If you use ChatGPT, it streams all the time. All chatbots stream. We've enabled a lot of streaming for not only the tokens, but all the events that may happen as the graph is kind of like executing. And I just want to finish by highlighting kind of like where LangGraph fits in within the LangChain ecosystem, because an orchestration framework, we believe, is a big component of building reliable agents, but it's not all that you'll need. You'll also need all these other components. You'll need the language models themselves. And so LangChain has, you know, a bunch of language models that lets you easily swap between language models, or more relevant for big kind of like multi-agent systems, use different language models in different places. If you want to use a small model here and a large model here, you can easily do that. Lots of other components for interacting with documents, models, things like that. And then Langsmith. So agents are hard, they don't work. You generally want to test them. You generally want to have great observability. Langsmith is kind of like a separate platform purpose-built for for observability and testing of large language model applications. Integrates seamlessly with LangChain and LangGraph, and that's kind of how it all fits together. So you've got Langsmith kind of like observing things throughout, allowing you to do debugging. You've got LangChain and LangGraph as these low-level kind of like building blocks, and then you've got a bunch of integrations for all the components that you might want to use. That is all I have. Excited to hand it off now.
Fantastic. Thank you so much, Harrison. Our third and last speaker for this session is Shreya. Shreya has done some amazing work on the intersection of HCI and machine learning, on HCI as well as on machine learning, on data management, you name it. I'm a big fan of personally her recent paper, which is called Who Validates the Validators? But yeah, we're excited to hear from her. So Shreya is a PhD student in computer science at UC Berkeley. Her research addresses data challenges in production pipelines through a human-centered lens. We are very excited to hear from you, Shreya.
Thanks for having me. Excited to be here, and great company. I've admired Omar and Harrison very deeply. So I'm a fourth-year PhD student in the HCI and databases group at UC Berkeley, and my advisor runs the EPIC Lab, where we build low-code and no-code data tools for social scientists like public defenders and journalists. And in my PhD specifically, I'm working towards intelligent data processing, specifically large-scale, domain-specific document processing. We don't have an open source system yet. We've been working on it for a couple of years, but hopefully it will come out this fall. And still we have plenty of things to chat about. So data processing, large-scale data processing is a pretty ubiquitous problem. People and organizations have data analysis teams that actually, consist of so many human annotators. So consider maybe a big hospital, right? There's all sorts of data in this hospital, maybe patient records, heterogeneous data, unstructured free-form documentation, for example, transcripts of doctor-patient visits, clinical notes, papers, and more. And machine learning can help do a lot of these data analysis tasks and not require humans to do it. But the problem is that it's hard, right? MLOps requires people to have custom models. It requires these domains to hire ML engineers, and it's just not scalable or feasible. So it's no secret, right, that LLMs are so exciting for us because now there's this promise to have one giant foundation model that can do a lot of tasks, these data processing tasks, with just simply a prompt that anyone can write, not an ML engineer. I think this really simplifies the ML lifecycle, and people developers across the world are figuring this out. Like we have a collaboration with LangChain, in which we looked at a number of their users' prompts, and there are thousands of these kinds of data pipeline-like tasks. So let me illustrate what an LLM-powered data processing pipeline looks like in its very simplest form. Here's an example pipeline to summarize doctor's notes and put it in some sort of structure and also strip away any personal or identifiable information. So maybe other medical professionals can read and analyze it. It's very straightforward, right? You just combine these two things together, ship it off to an LLM and an API call, and you get some sort of output summary. This might work great once, might work great twice. The problem is that LLMs make these kinds of unpredictable mistakes at scale that we were observing. So maybe the task is kind of hard with lots of instructions. And occasionally, 1 out of 10 times, you might notice that the instruction gets violated. The task is not the only axis of hardness. Data can be hard in a sense, right? Suppose we have a very long transcript. Maybe 1 out of 10 times it's going to mess up the PII instruction. Even the best of the best models, right, are not going to be 100% reliable all the time. And this is a very simple kind of data processing pipeline. What we're working with social scientists, these pipelines follow a MapReduce framework. So maybe these outputs are then grouped by the condition or grouped by the medication and then further aggregated or summarized by the LLM. So in the work that I've been doing, at least research papers we've been writing over the last year are really how do we think about improving LLM reliability at scale, which I want to define as following all instructions for any input document and alerting the user, maybe if there's no good output. And my background before the PhD is in machine learning, ML ops. This is how we dealt with ML reliability. We looked at the data, we did data quality validation. But the problem is that you can't do these same techniques for LLMs, right? There's no schema, there's no structured data, there's no data quality metrics that easily apply in this LLM world of free-form text outputs. The best solution that we have is this sort of vibe checks. So I really hope that, in this session, we really realize that LLM reliability is an interdisciplinary effort here. When we try to work across different domains, these are just the domains that I do research in. But I will very briefly talk about a couple of research works around scaling up data quality assertions, as well as how do you think about incorporating a human in the loop when doing these problems. The first aspect of this in the data management side of things is we recently wrote a paper on a system called SPADE that automatically synthesizes assertions for any custom data pipeline or data processing task. So taking our same document summarization example, where you're supposed to remove any sensitive information, what the assertions for data quality might look like is a structured view like this. We have some attributes that we care about, our outputs meeting. In practice, also, it's input documents too, as well as maybe outputs of retrieved documents if people are doing RAG. And these can be very easily bolted onto these data processing pipelines, and then you just retry the LLM and half the time it works again. The crazy thing about these non-deterministic systems. Or we can just surface them to the human in the loop when they're iterating on their pipelines. And the challenge here, right, if you're trying to automate this entire process of coming up with these assertions, right, is like, how do you write the good implementation? First of all, how do you come up with the columns in the structured view? Second is how do you write these, right? Some of them require coding experience to write, which our journalists are not going to write Python functions. And the other thing is, some of these are actually hard to evaluate, right? You might need LLMs to evaluate these attributes. So in our SPADE system, we kind of formulate this problem as generating a small set of assertions. So it's pretty easy. It doesn't add too much latency, with high coverage of low quality outputs and good accuracy. And there are two challenges there. One is how do you find these custom domain specific assertions? And then how do you make guarantees on the failures? And you should read the paper for that part. The thing that I think that we were most proud of was our idea for how we created assertion criteria. And we got this insight by observing people iterate on prompts, LangChain users iterate on prompts, as well as people in our user studies. So you might see somebody start out with that medical summarizer prompt like this. They might add an instruction to it. If the document doesn't have sensitive information, don't include it in the summary. They might keep, trying a bunch of things and so forth. And what this tells us here is, what does a human care about, right? All of these prompt deltas tell us the human cares about the output meeting a certain constraint. And then sometimes people are editing the same instruction, right? So that means the LLM is quite bad at solving this. And of course, there's a world in which people are not going to be writing prompts anymore, but LLMs themselves are going to follow this exact same prompt rewriting, right? Guided towards output, gold standard output. And people also iterate on their systems, right? So if people are writing components of large language model pipelines, they're going to iterate on those components, and there's still plenty of stuff that we can learn from what they care about. So we kind of categorized a prompt delta taxonomy to see, does this even generalize across tasks? Does this generalize across models? We did this for GPT-3.5, GPT-4, different fields like finance, marketing, and so forth. And we found that, generalized pretty well. And independently, actually, there is a Kai paper that created pretty much the same taxonomy. They just added one more category around hallucinations specifically as a category. So really, this can be used, and we use this to ground an LLM in generating, domain-specific assertions. And there's a number of questions, of course, here. What if these assertions are bad, if they're not going to work? What if they're redundant? So you should check out our paper. We worked with Harrison. It was a great collaboration and learned a lot of stuff from mining all of those runs. The second thing I want to briefly touch on before we do the short panel, sorry that we're taking so much time, is the HCI aspect of all of this, right? What does it mean to build an interface around developers creating these kinds of data quality assertions, and in our case, journalists or social scientists creating the right assertions for LLM pipelines? The main thing that we have been coming to is that soliciting human input throughout all sorts of LLM processing workflows. So maybe that's in the data processing itself, maybe that's in the assertion generation and filtering itself. That's exactly what we did in our eval-gen paper. And we got input from humans in two ways. One is people edit the assertion criteria. There's metrics, those columns that I showed you in that table in the previous slide, or humans also grade outputs, right? They tell us what is good and what is bad. And traditional UI principles that are in a HCI 101 really hold true in this case. And my favorite thing to tell people is we know LLMs have long latency. So can we line them up with human think time when humans are trying to grade outputs, when humans are editing criteria, so the experience is much simpler and people don't get very frustrated by the idiosyncrasies of these systems. And of course, there's a number of other usability heuristics that I'm happy to chat about. So I'm going to skip through this in the interest of time. We built an interface to help people iterate on these assertions. And the thing that we found the most surprising was that their assertion criteria drifted for not only the example task that we gave them, but some people brought their own task and then they changed their assertion criteria from grading outputs interactively. And unsurprisingly, they wanted to add new assertion criteria when they observed failure modes. But perhaps what was most surprising is they might want to go back and reinterpret existing criteria that they set before to better fit the LLM's behavior. For example, imagine that you're writing an NER named entity recognition pipeline or extraction pipeline, and you don't want hashtags to be extracted as entities. That is a criteria for you. You might start grading. This is exactly what like 3 of the participants did. They started grading. They kept grading bad, bad. There's hashtags extracted as entities, but once they started, seeing that many of the LLMs had this unique failure mode in which they were extracting entities that were hashtags, but not putting the pound sign before it. And then they thought, oh no, actually what I want is not to have a pound sign in the output. And they would go back, grade the examples as good. And then it's like, okay, so what is it that you care about, right? If these metrics are changing, if they're a function of LLM outputs, models are changing under the hood, right? What this implies that LLM sense making is just a natural part of human evaluation. And implications here are people have to be continually evaluating, grading, aware of how these systems are changing under the hood, especially when they become these complex or more compound AI systems. I'll skip through these parts. Please read the paper if you're interested in all the fun user studies. But the bottom line that we have been running into over the last year, and that we're continuing to run into, is that LLMs are just not reliable for a lot of different intelligent data processing tasks. But we could really make strides in this reliability by building human-centered solutions and constantly trying to think of unique and clever ways to put humans in the loop, as well as gain information from how they solve the problem. I'm happy to chat, and thanks so much.
Fantastic. Thank you so much, Shreya. I think this was a really lovely talk, and absolutely no need to apologize. I think all of us learned a lot. So now we'll quickly switch over to the panel with all of the speakers that we just heard from. And I have a few questions for each of you. In the interest of time, I'll actually stick to the questions we received from the audience, because I think we received some really great questions. Okay, so the first question, which was for Omar, but I think actually is for all 3 of you, which is, the question as stated is, a basic question I've had is with DSPy and the basic premise of programming, not prompting. It seems like on the one hand, the field is moving towards giving normal people the abilities that currently only programmers have. But on the other hand, we are also moving towards specialized sort of chains or specialized programming techniques for programming LLMs. So how do you sort of square this circle? How do you think of, I think this applies for all of your work, like how do you sort of deal with, on the one hand, making this more specialized or specific to a task, and on the other hand, LLMs and LLM products being touted as general purpose programming agents that can sort of give ordinary people the ability to write code. And I think we can take this in whatever order. Maybe we can start with Omar.
Yeah, I think it's important to recognize that this is a stack. And so I think the question actually, as I saw on YouTube, says something like, are you betting against the folks? And I think the person says the field, but the folks who sort of perceive the end of programming as near or something. Maybe I'm paraphrasing here. And it's like, yes, of course, I'm betting against the people that say programming is going to be over. I mean, have you seen the systems that exist right now? Now, it's important to recognize it's a stack. So in order for us to, a lot of things can happen in parallel. We can democratize a lot of machine learning. And this is especially true for repeatable tasks that are in the head sort of highly popular, simple things. And at the same time, we can make a lot of progress on building systems for things that are more sophisticated or advanced. And you need a lot of fine control to get existing language models and just deep neural networks in general to perform the tasks where you have a lot of constraints, where you have really complex sort of inputs and really complex outputs. And there is, we're not going to overhaul computer science. We're not going to overcome the fact that building modular software is, and composition and all these sorts of fundamental ideas are really the way in which we can iterate and help people iterate on that. And there's already a large number of people that know how to program and sort of care about their tasks. Now, programming is different from coding, and this is not my idea, but it's a good thing to keep in mind. So increasingly, maybe there will be a lot less code, but you still need people who care about a certain problem, like Shreya showed, like Harrison discussed, who know what it is that they want to do, or rather, who can sit in a driver's seat and work with a system to figure out what it is that they want, and iteratively sort of explore how to make their systems more reliable. That is programming, or at least that's part of programming. Now, as we sort of make these systems more and more reliable for repeatable tasks, we'll also certainly expose, we being the community at large, higher level abstractions, things that feel less like programming, things that eventually look like chatbots or like other sort of simple interactive systems. But that is going to be built on the advances happening through, maybe more machine learning, like more programming, like foundations. Is that my perspective?
Fantastic. Thank you. Any other thoughts? Maybe Shreya and then Harrison?
I lost context of the question. I'm sorry. Can you repeat your question?
No worries. Yeah, the question was essentially, how do you square these two opposing tendencies? One is giving anyone the ability to program, and the other is having these sort of specific experts sort of coming up with programming these LLM pipelines.
I think there's going to be a market for both of them. Like there's no one size fits all. And the nice thing about LLMs, right, is they make it much easier for people who aren't ML experts to at least get started. There are obviously going to be certain cases in which you should be an expert. You want to be an expert. There are Microsoft Excel experts. There are Java 7 experts. The number of them dwindles, of course, but they're there. What I think is increasingly interesting is how people have to be trained in system building to build some agents or to build LLM pipelines. And it's not like traditional computer system building. It's a new kind of systematic thinking that I think classes that universities are very well positioned to teach. I think that people are going to have to be trained to use LangGraph, trained to use DSPy. Fortunately, I work specifically in data processing with a certain kind of user who's not writing code. They're just writing our YAML files all day long. So I don't know if that's as generalizable, but I do think that there's some growing pains right now from LLMs being quite new. But I don't see this being as much of a problem in 5 years, 6 years when people are trained to use these systems.
Fantastic. And Harrison, if you have any thoughts.
Yeah, I mean, I think I've said this in a few different settings, but I think like with LLMs, a lot of it just comes down to like communication. And I think, and by that I mean very similar things to what kind of like Shreya said around system thinking. Like if you think about what you want an agent to do, you still need to communicate to it what you want it to do, and you need to communicate that in some form, right? Like we're all intelligent people, but if we went into, some shop and we're asked to do some random task, we'd need someone to tell us like how to do it and what the right way to do it is, and maybe they'd show us like a few times, and then maybe we'd do it and they'd give us some feedback, right? There's this like learning, and all of that's just communication about how to best do a task. And that communication can be in prompts, that can be in code, that can be in a higher level abstraction, that can be through like feedback. I think, but like at the end of the day, it's all just communication to these, LLMs, which we believe have the ability to kind of like reason. And, different things require different styles of communication, and you might use code for some of that, and you might use prompts for some of that, and you might use examples for some of that. And we're still figuring out the right answer, but, I think it all just comes down to communication.
I think that's a great segue to another question which we had from Michael Katz in the chat, which is, how do you deal with these sort of graphs getting extremely large for non-trivial tasks? So like these chains of communication, or do you expect them to be bounded in some sense? Do you expect like any sort of production use case to be within a certain size perhaps? Or how would you deal with like, this ballooning up of this graph?
Yeah, I mean, we start to see that a bunch, and I think the modularity of both LangGraph and DSPy is really helpful here. And this also comes back to like communication in some sense, right? Like at our company, like we have certain people who are specialized in different things, and we have one team for front end engineering and another team for marketing, and they have different communication and ways of learning things. And if there was a new person onboarding onto those teams, that have a different way of teaching them how to do that. And so I think as we see these, like we're definitely super early on in all of this, right? Like let's not get carried away. It's still super early on. So yeah, most of the things we see going into production, like are not these like crazy like 1,000 node chains, but we do see some that are like, taking like 30 minutes to run or something like that. So we're starting to push the boundary, and 30 minutes still isn't even that long in the grand scheme of things. But yeah, I think as things start to, one of the big things that we've invested a lot in, and I think you can do pretty easily with DSPy, correct me wrong, Omar. Everything's just like modular. It's just a module. And so it's a subgraph in LangGraph, or it's a module in DSPy, and you can compose them in a lot of different ways, and that makes it really easy to compose all these things together. And so that's a pretty common pattern we see as these systems get bigger and bigger.
Fantastic. Any responses to that, Umar or Shreya?
I agree. It's pretty good.
It's perfect. I love it when the panelists all agree. Okay, so I mean, at this point, I also had like a question again from Michael in the chat, which is, isn't this sort of restricting ourselves to problems that we know how to solve? And actually, maybe this is a question for Omar and the lessons from MediQA. That was the challenge that you mentioned. Like, how do you think of this trade-off between automating tasks that we know how to solve versus breaking new ground when it comes to applications of agents?
So I think this is an important thing, which is generality versus specialization. And I think a factor, an implied thing in today's discussions, at least that's my position, but I kind of also gathered it's not necessarily too different from the positions that Harrison and Shreya might have, is there is so much potential in solving actual specific problems. And I don't think any of us says you should only solve problems you know how to solve. It's more like you have a problem you want to solve. It's generally a concrete thing. And we will want to help discover the methods, the iterative processes, the tools, the abstractions, the things that could help you iterate until you've tackled that problem. Building general AI is another thing, building AGI, let's say, or just kind of having a system that can solve all sorts of problems as it sees them. I mean, it has long history in general, maybe not necessarily just the term AGI, but just building general agents. That's a very different thing. We're very, very far away from that is my position. And I'm not saying it's not interesting. I'm just saying that we are far away from that. And, there is so much, because in practice, the people that want to solve problems care about their individual problems. We actually get a lot of things for free, because as long as we help them tackle these tasks. So I like to say that in my work, and I think this probably very much applies to the other two speakers, I think about general ways to help people solve specific problems. And I think that's more productive than only doing the general progress type. Now, we need language models, we need foundation models, we need things that are pretty powerful in a general way, because that's what we specialize. But on their own, it's not enough.
Fantastic. And I love your tweets about API being achieved, artificial programmable intelligence, as a substitute for AGI. I think that's a great way of looking at task-specific agents, and that's really where I think a lot of the progress will be as well. So I agree with you on that. Our next question is for all three of you, but maybe mostly for Omar and Shreya, which is, how do you make your project sustainable in a way that is also useful for real-world research? So PhD students are not incentivized. Many of the projects that start as academic projects really have a shelf life because the incentives are to do new work and not maintain existing work. So how do you think about that? Maybe we can start with Shreya and move on to Omar.
I mean, I think Omar is an anomaly here, being like an academic who's able to maintain such a great open source project. Like, that is certainly extremely difficult to do as an academic. I know how much time open source takes. The reason that I haven't really invested in it, especially because I'm only fourth year now, is it just doesn't feel like the time. We've been working on the same problem for almost 2 years, with like one use case of, Berkeley journalists are trying to tell stories about police misconduct. And for this, they're analyzing lots and lots of, PDFs of police data, trying to find like maybe there's a police officer who has been made like violating a bunch of laws, but somehow is like running from department to department unnoticed. But with data, in theory, you can find it, but there's just petabytes of random photos and PDFs and stuff to kind of mine through. And I think this is just such a classic example, like such a hard problem that many social scientists have, and they pay a bunch of people hourly to just sit there and annotate data. So I saw a comment about automation. Like, I think automation really, really like changes lives for these people, and makes certain kinds of intelligent processing much more feasible. I started out wanting to write an open source framework for this. And we are writing it. It's just taking a really long time because ML models have changed so much. The way that we think about, task decomposition has changed a lot. The context windows grew a lot, and I'm not an ML research trained person, so I didn't really know what that meant. It turns out that even if the context window is infinitely long and you stuff a bunch of documents in there, the quality of the output might decrease, right? So there's now ways that we have to think about optimizing for output quality that don't, linearly map to context length. They're not similar across model providers. The optimization frontier, if you were to think about from a database perspective, right, you can't even consider what a processing plan is going to cost and how accurate it's going to be. So I think solving a lot of these problems is just really, really hard if you want to think about generalizing it. And I don't know. Hopefully I will release something this fall. That's my take.
We hope so as well for all of our sakes. Omar, any thoughts on that?
Yeah, everything Shreya said. And then I do want to comment on a sort of implicit assumption in the question about incentives. I mean, I actually disagree. I promised a blog post on this. I've actually written most of it. I should come out soon. But I don't agree that incentives are not aligned with grad students. This is specifically about grad students, but frankly, it just applies to anyone in this space who just wants to prioritize things. I don't agree that incentives are against open source. I think what happens for grad students, and I think you can generalize this to others, is that when we start, there's a lot of emphasis on publishing your first few papers, and that's how you learn to do research, that's how you demonstrate progress. But once you've done that, you actually realize, or you should realize, that career growth, your own fulfillment and happiness depends a lot more on just what sort of direction or paradigm or area or big project, bigger than papers, bigger than an individual paper, you're leading and you sort of are trying to affect change through. And when you're sort of doing this, you could do this through many things. Open source is just really nice at structuring this. So like when I work on the SPADE, it's not isolated from my research. Almost everything is part of a paper or another. In many cases, I'm not the first author in all of these papers. Sometimes I'm the last author, sometimes I'm a second author, sometimes I'm somewhere in the middle. But basically, like a project can grow in a modular way that integrates with the individual sub-projects or papers. And that can be really, really sort of more fulfilling than doing separate, isolated papers whenever possible. Of course, there's a burden and there's sort of certain things that go into certain amount of time that goes into an open source project. But I think it's pretty rewarding and it creates a lot of opportunities. I mean, I think Shreya, just given her closeness to a lot of the applications, just very proactive. Like she gets a lot of these advantages even before she releases an open source project. But for most people, I think it gives you access to good problems. It gives you access to a kind of a reality check. Also, are you doing things that are actually useful? I would say one of the hardest things is sort of the kind of mental shift about priorities and whatnot. For example, a lot of us grad students specifically, but again, this applies to other people who are excited about the thing itself and less the release. And I think Karpathy has a really cool kind of tweet about you need the thing and then you need the ramp. People can look that up. So sort of is simply releasing your code with a little README is not enough. You need to make your release usable. You need to make it useful, which is different. You need to make it approachable, which is even more different and hard in other ways. And then you need to recognize at some point that your user base might not be the one you started with initially, and you might want to not block users. When I started DSP early on, this is something I really learned a lot from Harrison about. I was thinking of grad students and machine learning engineers as the primary set of users. And what we saw from Harrison and from LangChain is that they were able to massively expand the set of people that are, they're still programming, they're still sort of writing code, they're still pretty technical, but they are sort of interested in building systems and solutions. And so right now, probably more than half of our user base are people that used to do, things that were not machine learning before. So I think these are the sorts of really engaging and fascinating questions that you get to explore. And I really disagree that this is not incentivized. I think nothing sounds better when you're sort of presenting your work than saying, I have this coherent theme that sort of people are finding useful and hopefully having positive impact. And I hope to see a lot more of that in general. And of course, there are many successful instantiations. I'm thinking, for example, of Tim Dittmer's, his work on QLoRa and other things, or CLoRa, and other similar really cool stuff.
Fantastic. Thank you, Omar. The next question is for Harrison. So the questioner asks, I wonder if LangGraph is related to the talk on evaluation earlier. What is your favorite tool for evaluation on language agents, and how do you think of evaluating systems rather than just models?
Well, I'm very biased because we have LangSmith that we make, so I'm obviously going to say LangSmith is my favorite tool for evaluating. But yeah, I do think it's related in a few ways. I mean, one, when you think about evaluating, when we talk with companies, a lot of them want to evaluate. We wrote a white paper on this, but there's kind of like three things that when people talk about evaluating, they talk about three different stages. One is kind of like typical kind of like, test set that you have offline and you run before it goes into production and it scores like 90% or something like that. The other is like online. So like when it's online, you get real user questions. Can you evaluate them real time and get some sense for how it's doing? But then a third way, which actually a surprising amount, at least to me, a surprising amount of people meant when they were talking about evaluation was like during the application itself. Like if you can evaluate and tell that a user's question is off topic or toxic, then you want to act on it in the moment. You don't want to do it like you don't want to do it during online evaluation as part of the background flow, and you don't just want to have it as part of your test set. You want to have it as part of your like system that checks things. And this is where I think frameworks like LangGraph and DSPy can come in handy because they put those evaluations as part of the system. And that's also where you need like really good controllability. And you can maybe have a small language model doing this detection, and then you pass it to the agent or something like that. So I just flag, like, I think LangGraph and system and orchestration systems like LangGraph and DSPy help add in evaluation like things to the flow. And then like I think a lot of what we focus on at LangChain and with LangSmith is on evaluation of LLM systems, not LLMs, and maybe highlighting just like a few things that I think make this or where the difference lies. Like one really important thing for one really important thing for LangSmith has just been the ability to see the whole trace of what happens. And that is really important for systems because obviously in systems you have a lot of different things going on. And that's also, I'd absolutely call a form of evaluation. That's like human evaluation. That's a human looking at it and getting a really good sense for what's going on and being able to understand it. And Shreya talked a lot about HCI components. And I think that's like absolutely both for developers, but also for end users. That's one of the most interesting spaces, hands down, right now, I think, in the field. And so like these traces I just flag as like one thing that we emphasized a lot, that you maybe, if you're just looking at LLMs, maybe just having the input and output is great. But if you're looking at systems, you need the whole kind of like trace. And then for like evaluations, I think there's different styles of doing it. You can kind of like treat it as a black box and just look at the output. You can one of the commonalities that both DSPy and LangChain, LangGraph have, I think is emphasis on tracing basically, and tracing all the steps. And that's important for visualization, but that's also important for evaluation, because if you have those traces, you can then evaluate the whole trace of the agent. And like maybe it arrived at the right answer, but it went in a loop for 10 things asking the same question. And that's kind of bad, right? So I think like having those traces is also important for different types of evaluation. Evaluation, I'm sure we could all talk about for like an hour as a separate topic, so I'll stop there. But yeah, super interesting and very relevant.
Evaluation is actually the theme of the second session, so we will talk about it for an hour, but thank you so much, Harrison. I think we're out of time. I have a few very short, like quick fire questions for each of you, which are about technical details of your work. So maybe we'll take 30 seconds per question. Okay, so Shreya, this is a question by Damien. Who validates the validators is a great paper. How is the human review calibration performed? Is it through few shot examples only?
It's in the paper, we don't even do any few shot examples. We just synthesize a number of different validator prompts and we just pick the one that has the highest accuracy. with the human graded examples. In the second iteration that a couple of undergrads are working on, there are some few-shot examples that are being used, but that's basically it. We did think about doing using DSPy. I think the ergonomics are challenging with a TypeScript-based framework system that we're building, but hopefully DSTS will come out. I don't know.
Fantastic. Then for Omar, this is interesting because I know you have a paper on this, Omar. What are your plans for integrating prompt optimization with weights fine-tuning?
This is an active area of research. We do have, in fact, a nice paper called Fine-Tuning and Prompt Optimizations, two great steps that work better together, and they do work better together, which was surprising. So it turns out if you only pick one, prompt optimization in many cases is better unless you have tons of data on which to collect traces and to do RL. But combining the two is pretty cool. Now, it is harder to use. Fine-tuning generally needs a lot more infrastructure. And so we're spending a lot of time improving that infrastructure. So for example, you can now fine-tune, through providers like OpenAI, but also we're setting up a lot of sort of systems so you can fine-tune in your own GPUs, which is something that, for example, many academics want to do in a way that is less annoying. We can do it today. That's what we've done, but it's there's a lack of good infrastructure for scheduling these types of jobs, in the way that we need it in DSPy. But yes, there is already a lot of effort in this space. It's pretty simple. It's less sophisticated than prompt optimization, and you should expect a lot more. Or just start research efforts and open pull requests with your optimizers.
Fantastic. And then for our last question for this panel, Harrison, we have a question which says, how would you describe the key differences between DSPy, LangChain, Llama Index? Like, what is like a clarifying example for you?
DSPy in particular, I think is very unique in all the work on optimizers. And I've chatted with Omar a bunch about this. I think that stuff is awesome. I would love a way to hook into the optimizers from LangGraph and LangChain. I think that is absolutely kind of like a differentiator. And then I'd also shout out one other framework that I think is differentiated. Instructor by Jason Liu, I think, is pretty differentiated, namely in its kind of like simplicity and its kind of like design principles that it takes. It really just is wraps very minimally around an OpenAI client, which I think is not something we did and not something we could do, but I have a lot of kind of like, I think DSPy and Instructor are two frameworks that I look at that I think are differentiated among the 60 or so that are out there.
Fantastic. And I think with that, we'll close out our first session. Thanks once again, Omar, Harrison, and Shreya, for all of your wisdom, all of your time. Our next session will start in about 10 minutes. So at 12:45 p.m. Eastern, we hope you have some time to get some water, catch a break, and we'll see you back here in 10.
All right, welcome back, everyone. I hope you had some refreshing water and a short break. And now we are back with actually our second of 3 panels today. And I couldn't be more excited to introduce our panel on evaluating agents for a real-world use, in which we will talk about how to build benchmarks that are adequate for evaluating real-world utility, the best practicing of evaluating AI agents, and also here the attempts to evaluating actual real-world harm that can come from using AI agents in production. I'm thrilled to announce the speaker lineup we have to discuss these questions. We will hear from the creators of some of the most recent and influential benchmarks, as well as the creators and developers of the infrastructure to run model as well as agent evaluations. So let me kick it off first up with Karthik Narasimhan, who is a professor at Princeton University, as well as the head of research of Sierra. Again, we will have all the bios in the chat, as well as the social media handles. Feel free to ask questions already during the panel discussion, during the talks, that I can pick up then later in the 30 minutes we designated to Q&A. So with that, Karthik, the stage is yours.
Awesome. Thanks, Benedict. Just give me a minute. Does it look good?
Perfect.
Awesome. Thank you. Well, first of all, thanks to the organizers for putting together such an interesting and exciting workshop. So what I thought I'd kick things off for the session is really talking about, benchmarking agents for the real world, and kind of like Benedict mentioned, this is, the stuff that I'm going to talk about is influenced both by my experience, building from the academic side at Princeton, but also recent experience, at Sierra, which is a new company that's trying to build conversational AI agents for the enterprise, right? So both from the practical point as well as from the research side of academic research side, I hope to give you some insights and hopefully have some discussion after that. So to sort of begin, I thought I'd provide a quick chronological historical summary of how I've been personally thinking about agents, and sort of lead to the point where I can sort of make some learnings that I've seen over the years, and also think about how that can affect what we do in the future, right, in the near future as well as the long-term future. So to sort of start it off, right, so the year was 2015, right, and this was a time when DeepMind had just released the great Atari results, right? So they were able to develop RL agents that could play Atari at a superhuman level. And a friend of mine, Tejas, and I, we thought, hey, we're interested in NLP, language processing, and reinforcement learning, and decision making, and things like that. Are there sort of benchmarks or tests we can sort of devise such that we can test an agent at both its language understanding capability and its decision making, right? And just so you know, right, like there did exist some kind of tasks, like instruction following was a very big major part back then, but there wasn't anything that where the state really depended on language understanding, right? So we did this thing back then where we said, okay, text-based games are a great environment here. Basically everything is in text. You have to understand. This is a great test for developing better language models, better agents, and so on. And so that was 2015, right? And I was actually quite surprised by how it picked up. There were sort of lots of efforts following that. Microsoft, especially, big shout out to them. They made more and more usable benchmarks based on like TextWorld, Jericho, and so on. And it ended up being quite a decent test of agents that could understand natural language to some extent, and be able to use that towards their decision making, right? So it was nice to see that. And then, we kept working on it because there were not really good alternatives. And also because, this was back in the day when, if you're old enough to remember, we were still looking at LSTMs and so on. And in 2020, around that time, right, GPT-2 had come out the previous year. And we started thinking, hey, language models are getting better, right? And a lot of the previous agentic systems that were built on these text game environments were probably not utilizing the generative capabilities of these models, right? So this was in 2020 when one of my students, Shinyu, he basically had this idea where we can use language models not just to pick actions a la the traditional RL approach, but actually generate actions, right? So we ended up using something like GPT-2 to generate phrases in these text games, right? And this was also during that time, during the same time, there was other work that came out where people are building on these text game-like environments. There was a very nice data set on NetHack, right? Which again added more complexity and so on. So all this was great, right? So we were using text games as this benchmark for language-capable language agents, but it didn't seem enough, right? And based on some introspection, what we sort of thought was, we need to move towards more real tasks, right? So this is the main part that was missing was the fact that, hey, you can develop an agent to play a game, but then what, right? There was sort of like this disconnect between agents that you're building for these games and what you can actually do in the real world, right? And so in 2022, we sort of thought, okay, what is more real than a game? And this led us to think about, web as one kind of an environment. So we did this thing called Web Shop, right? Where agents can read stuff on the internet, on web pages, just like the internet, and be able to take actions and so on. And again, the community started, taking that into stride. And, we saw lots of cool benchmarks on top of this, like Web Arena, Mind2Web, Agent Bench, and so on, right? So again, moving towards more and more realistic tasks became a thing. But I also just want to point out, it just recently became a thing, right? So we've been working with sort of these more synthetic, smaller scale benchmarks for a long time. And then as language models became better, right, starting from GPT-3 and so on, right, we started seeing this explosion over here, right, just 2 or 3 years since, right? So where we've seen more and more realistic benchmarks. And so I just want to point this out because I think that this trend is great, and we should be moving towards more and more real benchmarks. And this is something that's very, very recent, right? So we still have to think about what that brings, right? So this more complex real world tasks, what does it mean to evaluate agents, right? It's not simply a matter of just checking success rate on the task itself, right? These new realistic benchmarks require more multi-dimensional measurements of various things, right? And so what I want to sort of show you is a few of these examples, that we've done recently, and talk about what we've learned from there. Also give an idea of like what we could do for the future. So based on all of this, right, seeing this trend, what the sort of high level question becomes, what do we actually want in real world agents, right? So imagine agents that you're going to put in production, right, put into the real world that are going to communicate with other agents, whether they're human or artificial, right, and be able to actually plan over long horizons, take these action sequences that are more than just a single action, right? They need to be able to follow rules or policies, usually specified in language. And then the reason I'm saying language is because that's the easiest way we can communicate what we want, right, as humans. And there's sort of like a third point that we really want these agents to be able to do is perform tasks in a reliable, consistent manner, right? So this third point, especially, I'll show you, is something that we didn't really consider, right, before the last couple of years, because we didn't have benchmarks that really looked realistic, right? Whether you want to check reliability in a text adventure game is really something that doesn't really come to mind, right? So I'll give you a couple of examples. So the first benchmark that we recently did that tries to resolve, especially point number 1 over here, was something called SweBench. And how SweBench basically started was, Carlos and John sat together with me, and we were like, okay, what is a really real world task where, we can make use of agents and make it such that, they can cause a big change, right? And so SweBench is essentially a very simple sort of thing that came out of that, where we're basically saying, okay, software engineering as a task itself is not just about generating code, right? So language models are getting better at generating code, but that's not really what software engineering is, right? So if you think about what a software engineer does, there's a lot more things, right? And so SweBench, in a nutshell, tries to capture one particular aspect of this, which is like trying to find and resolve issues within a huge code base, right? And we think this is a good example of a very realistic task where agents are required to parse information from all these different places and be able to actually post a good patch. And as we, just to give a sense, right, SweBench is still sort of far from being solved. The top models and agents on these are just under 20%. So lots of things to be done. And so the other kind of point that I talked about is this point about reliability, right? So like I mentioned before, real world utility depends on more than just success rate, right? And to sort of capture that, another piece of work that I think would be interesting for people to see is work we've done at Sierra, which is TauBench. And the sort of background behind TauBench is, we're thinking about, in real world use cases, agents actually have to interact with human users, right? So a lot of the benchmarks that we have prior to this, only look at agents interacting with some environments, some tools, and not really too much with the human, right? There's of course a lot of work in dialogue systems, but that was before LLMs got good enough to the point that we can actually simulate users and generate dynamic, realistic conversations, right? So TauBench sort of combines these two things, right? So an added layer of realism, if you think about it, right? Where we both have a user and an environment, and an agent has to adapt to both of them. So I'll just quickly summarize, what TauBench actually shows, right? So the most interesting finding that we found, other than the fact that most of the frontier models do pretty badly, is that there's notion of reliability is something new, right? So if you look at this figure over here, the x-axis just shows you running multiple trials of the exact same scenario. So a scenario could be something like, a customer wants to return something from their previous order and then buy something new, right? So something's as simple as that, but you can have different sort of lexical variants of that, right? So the way the conversation can evolve for the exact same scenario, you can have 10 different variants. And so what we did was we just ran the same variant, same scenario with multiple variants. And you can see the ability of an agent based on these state-of-the-art models, right, to a function calling agent to reliably complete every single task in a particular scenario is very low, right? And this sort of drops, this quick drop in this performance is something that's quite interesting. And I think we need to be able to fix this, right? So ideally, for real-world agents, I mean, the number at x equals 1 matters, but ideally we want them to be flat lines, right? So we don't want the performance to degrade, because if you think about real-world agents, they're going to be doing the same tasks hundreds of thousands of millions of times, right? And you want to be having that guarantee that they can actually do that task. So I'll sort of skip this, but there's some failure points that we note in the paper, but to sort of like bring back to this picture, right? So I think we are sort of on this upward trend of building more and more realistic benchmarks, and we should be continuing this, right? And this also introduces some challenges, right? So the complexity of some of these tasks as they increase, we also need to be careful about how we evaluate agents, right? So not just looking at, again, the one-dimensional thing, right? There'll be aspects of reliability, cost, and so on that'll come up, and this is something that we need to be looking at very carefully, right? And why we're all doing this is basically, to move from the sort of demo agents, which are easy to build, but really hard to get to that 99.9% reliability, right? So this is something that might resonate with some of you, right? It's quite easy to build on top of these LLMs, but to actually get it into production is a quite totally different thing altogether. And we need to be able to build good evaluations in order to, have that reliability in our agents that actually go into the real world. So I thought I'll sort of just end with this sort of high-level guiding principles that I've learned over this whole journey. I think number one, we need to make sure, because these models are getting so good, we need to be putting a lot of effort into making sure we can move towards more and more realistic benchmarks, but then also make sure that they're measurable, scalable, and easy to use, because that's going to be critical towards ensuring that we make systematic progress in making our agents better and continuously improving them. I'll stop here.
Thank you so much, Karthik. Thank you for sharing those insights. It's really great to hear all the work that you've done in recent years in this space, and also how the state of benchmarks kind of progress towards more and more realistic tasks. Great work. I think next up is Haley Schulkopf. Haley is a research scientist at EleuthAI and one of the core developers of, for example, the language model evaluation harness that powers for example, the OpenLLM leaderboard, and is also an open source effort for everyone to use. So Haley, take it away.
Yeah, thanks so much, Benedict, for the introduction. So I'll try to keep this brief so we have more time for questions, but I'm just going to talk a little bit about what we've learned when evaluating just base language models and how that can potentially sort of influence how we think about agent evaluations. And so in particular, I'll be touching on the point that Karthik had last on those bullet points, reproducibility. So for context, I work at EleuthAI, which is a small nonprofit doing research on AI, but specifically large language models. The LM evaluation harness is a library that EleuthAI created around 2021, which is, I guess at this point, ancient history for sort of large language models, just to sort of replicate the few-shot evaluations described in the GPT-3 paper, to sort of test on like new, smaller open source models to see how they measured up against the smaller GPT-3 sizes. And since then, the library has grown to be sort of a general tool for performing zero-shot and few-shot evaluation of like base and instruction-tuned language models in a prompted format. And especially since the past year when it was adopted as the backend for the OpenLLM leaderboard, which you might be familiar with, and just when sort of the Llama models released and there was an explosion of interest in open source language models, it's been used by a lot more researchers to predominantly sort of evaluate open language models on a set of standardized zero and few shot tasks. So sort of the key benefit here is reproducibility. But why does that matter, and what do I mean? So by reproducibility, I mean basically the ability to have confidence that when we are evaluating a bunch of different models, either just comparing against them or sort of looking at all the evaluations carried out in some subfields, that these are sort of comparable and could be replicated by some other researcher. There are sort of a number of things that might cause problems for reproducibility. These could range from sort of high-level decisions in how an evaluation is implemented, like say, whether we allow the model to generate a chain of thought before giving its output, or whether we do something like measuring the probability a model assigns to some given multiple choice answer set to determine an answer. It could be sort of a very tiny difference that might be just like a small implementation detail, like, for example, when we calculate metrics for the popular MMLU benchmark, when we take the average over these sort of 57 different subjects that MMLU tests, there are two different conventions. One used by the original authors is to average at the document level, and another that sometimes crops up is to average at the subject level, where we take the per subtask accuracies and average these. And this can give us something like a 1 to 2% difference in absolute percentage points on the benchmark, which can be sort of far outside the range of what we expect like normal variation on the benchmark to be when we rerun it for a given model, or can just sort of exceed the amount by which we're trying to select which model might be the best on the OpenLLM leaderboard, for example. There are other aspects as well, like say how we select few-shot examples. As Omar mentioned, GSPi gets a lot of benefits from optimizing which examples to present to the model and which order and how to present them. And this can have a huge outside impact on performance. And other things under the hood, like how we control for evaluating models with different tokenizers, whether we want to not think about tokenizers at all or consider them part of the system that we're evaluating, and so on. And so all of these details are seemingly small, but have an outsized impact. And it's not just the case, as I mentioned before, it's not just the case that sort of different implementation details impacts the numerical scores we get out when we evaluate models. It's also the case that they impact sort of what our findings are when we run a given experiment. So this picture is from a great paper that uses the eval harness for experiments called When Benchmarks Are Targets. It takes a few different prompt formats for the MMLU data set, one of which is the one that's sort of canonical by the original authors and is used in the OpenLLM leaderboard, and a few others that are plausible but aren't used. Basically, when you choose a different, like similar, reasonable prompts when you score the task, it's not just the case that the numeric scores for each model change, but actually these rankings that are produced end up being very variable. And so basically, our scientific conclusions are impacted by inconsistencies in how we implement our benchmarks, especially if we're trying to compare different like evaluation numbers from different models that were run under different settings. And unfortunately, it's also the case that language models are brittle, but more than that, that they're brittle in ways that are not necessarily intuitive to humans. So the example in these two pictures, this is two different prompts that you could sort of feed into a language model when evaluating coding performance on the human eval data set. The one on the left just sort of provides the input up to the doc string and then ends right away. And the one on the right has the same content, except there's a trailing new line and a tab character in the second one. And if you evaluate a typical language model like Llama on these two different sort of prompting styles for human eval, you might get a difference of like 5 or 10% in some cases, where this prompt on the right will be like that much worse on the task, just because sort of it impacts what types of tokens the model can produce, given that it no longer can produce like a token that starts with the tab character. And so sort of the net outcome of this is that all of these implementation details are potentially highly consequential. And at the same time, like it's sort of difficult to know beforehand that we've exhaustively like checked and known for a fact that we've like implemented our task the same way across two different code bases without sort of messing up on one of these important details. And so like as a result of this, like a lot of evaluations done in research in this field are sort of miss out on specific details among like some of the ones that I listed or others, where they just fail to sort of mention which choice they make. And sort of any of these choices might be defensible, but what their sort of reasonable default that they don't need to disclose is might be different from another person's sort of standard practice. And so papers, like very consequential works, often sort of under-describe what their evaluation setup is for a given task. Or when they do describe it, they might offload this description saying, oh, we follow this paper from these authors from the last year for evaluating this task. And so like new practitioners sort of have to trace the web of citations back to find out what's the source of this evaluation implementation, and do I trust this methodology? And then as well, sort of assume that nowhere in this link of like citations where each person sort of potentially re-implemented the benchmark from scratch, we have to assume and just like take it at its word that no like link was dropped here and no implementation details changed over the course of the cycle of re-implementing the benchmark. And so we've got this sort of butterfly effect where it's very difficult to have full confidence that none of these important details were missed by new researchers. And so this is really where like standardized evaluation tooling and libraries come in. It's difficult to sort of list out all of the key implementation considerations we might want in order for full reproducibility. But if you release your evaluation code and document it along with things like prompts and sort of commands to run it, this can potentially be a sufficient description of your evaluation practices and is maybe the easiest way to reach this bar. And standardized evaluation tooling like the eval harness or Helm or UKAC's inspect library make it a lot easier to comply with sort of being confident in your task implementations and also releasing these for inspection. Since it's hard for sort of small teams or newer practitioners to sort of implement and discover what the correct, so to speak, implementation for each task is. And so it enables researchers to do work at sort of a higher level of abstraction and lowers the barriers to entry. Yeah, and so if you're interested in more of sort of the challenges we've encountered, there's a great tutorial, or I shouldn't say it's great. There's a tutorial we gave at ICML, which the slides are public here. The evaluation harness is also open source, freely available. And we also wrote a paper discussing some of these challenges called Lessons from the Trenches on reproducible evaluation of large language models. Yeah, thank you.
Thank you so much, Haley, for that wonderful talk. And it's good to hear all of the shortcomings that you've already addressed with LM eval harness. And some of them we again see now for the agent work, right? So next up, the third speaker in our panel is Jelena Luketina from the UK AI Safety Institute. She's a research scientist there and is working on the agent evaluation work that the UKIC is doing.
Hi, thank you, Benedict. I hope you'll hear me okay. In this talk, I'll be giving a short introduction to AC with a particular focus on our work in evaluating models for real-world harms. So what is even AC? So it is a research organization within the UK government's Department for Science, Innovation and Technology. And our mission is to equip governments with, next slide. And our mission is to equip governments with empirical understanding of the safety of advanced AI systems. So next slide again. Next slide. Yes, one before. Yes, so we are a bit of an unusual org, which is why I'm giving a bit more background than usual. So we're built like a startup within the government, where we're more agile than the rest of government by design in order to deal with the fast changing technology like artificial intelligence. We have over 40 technical staff at the moment, and we're growing pretty rapidly, with some of our staff having worked previously in top industry labs. And we have advisors from both national security world and machine learning academia. And we do a lot of our work in collaboration with external partners like nonprofits and academic labs. We have over 20 such partnerships at the moment. And funding-wise, we're well equipped to keep doing our work and keep growing. Next slide. So at the moment, most of our work is on development of safety evaluations with several teams that are focused on different kinds of potential harms from advanced AI systems. So here's some of those. So one of those domains is misuse, where we're trying to assess the extent to which AI systems could meaningfully lower barriers for bad actors whose aim is to cause real-world harm. There are currently 2 such work streams. One is focused on cyber domain and one on chem bio. Then there's a work stream that is concerned about societal impacts of AI. This means measuring any kind of direct impact of advanced AI systems on individuals and society. Then there is a work stream which is concerned about autonomous systems. Well, specifically, it's concerned about risks from advanced AI systems that are deployed autonomously or semi-autonomously in the real world. And a lot of the risks that this work stream is concerned about are kind of less harms themselves, and they're more about like agentic capabilities that are harm multipliers for other kinds of harms. And then there's the safeguards work stream, which is evaluating the strength and efficacy of the safety components of AI systems when tested against diverse adversarial strategies. So for example, testing the large language model safeguard systems against a variety of jailbreaking techniques would fall into the work of this work stream. Next slide. Oh, sorry. No, the one before. Yes, and now across all of these areas, we're using a variety of different kinds of evaluations. So there are kind of classical question answering benchmarks that we're using. They're testing models' abilities and knowledge. These evaluations are relatively shallow indicators of capabilities, but they're very easy to administer. There is red teaming work, red teaming evals, which are usually of the form of free-form testing by domain experts, who then spend time interacting with the model to subjectively assess a model's capabilities. Then there are the human uplift studies, which are pretty much kind of the gold standard for misuse threat models, where we assess how much are AI tools helping bad actors in carrying out real-life harmful tasks compared to the use of kind of standard tools like internet search. These are kind of like really good kind of for misuse kinds of harms because they more directly assess the counterfactual impact of large language models. And lastly, there are the agent evaluations, where we assess models' abilities to use tools and operate autonomously and executing particular kinds of tasks of interest. Yeah, this is the work stream I'm a part of, and I will talk about more later. And so building kind of a sense of structure to assess agents has been really important for us because we also expect that as language models become more capable, we will need more and more agent evaluations across a variety of domains that we're mentioning here. So next slide. So we already redesigned and conducted evaluations across all of these risks areas. We have done both post and pre-deployment testing. The recent public example of pre-deployment testing is testing of the Claude 3.5 Sonnet. Most of the time, we share these results with the companies whose models we're testing and USAC, with whom we have very close collaboration. But some of the times, at least in May, we shared some of those testing results on our website, which you can check out here. Next slide. Another thing we're working on is building the evaluation infrastructure. So the one thing that some of you might be familiar with is the Inspect platform that we internally built and then open sourced, which for kind of running evaluations, and it includes a variety of facilities for things like prompt engineering, tool use, multi-turn dialogue, any kind of custom scoring, trajectory viewing. And in general, we find it really helpful. It simplifies building and running evaluations. I very much kind of encourage people, if you are working on building or running evals, to try it out. There are new features coming out all the time, and our team is pretty responsive to feature requests if you get in touch with them. Next slide. So, this is just the example of what it is like. What does the trajectory viewing look like with Inspect? Okay, so the next slide. So next I will be taking a closer look at some of our agent evaluations. The 2 work streams that primarily use agent evaluations are obviously autonomous systems, which is for whom that is the primary focus, and then cyber work stream for misuse. Next slide. So this is kind of a structure that is structure of our work that is used by most work streams. And here I'm going to give examples from cyber and autonomous systems. So here's kind of like what our workflow looks like. So first, there is like usually a team, or it could be the same team that's like developing evals that works on identifying potential risks. These risks can be very specific, and these are kind of like risk models and risk scenarios. Example of this could be, automation of the cyber attacks, or models self-proliferating, so like copying their weights and avoiding oversight. And so once we have those risk models, we are trying to design evals that measure whether, so once you have a risk model, very often you're going to either try to measure directly whether the model can do the whole attack, or is it in the whole scenario. But very often you're going to kind of try to break it down into specific capabilities that you think are necessary in order for the model to cause harm. And then you're measuring those capabilities. So the way you're measuring those capabilities is using the evals. So the evaluations that we use, some of them are public. So for cyber, we would use capture the flag tasks, or maybe if we care about the model software engineering capabilities, we might use SweetBench. But it's really also important to use private tasks, because as you know, the models can be trained on the public task, and it's important that we get like a correct assessment of the model capabilities, which is why, we have like a library of private tasks developed either internally or by our collaborators. And another very important part of evaluations is doing kind of correct capability citation, because there's always a risk that we are going to underestimate what is model actually capable of. And so it's important that internally we track roughly, our internal agent has to be kind of as close as possible to the state-of-the-art agent. And very often we might need to have like domain-specific agents. But also ultimately, what are we testing depends on the threat model. So if the threat model is that like there's a novice that just picks up, whatever like off-the-shelf agent is, then that is what we should be testing. And if we're trying to kind of get a sense of like what is the worst harm that one can do with like much more resources, then we kind of need to go really, really hard with capability citation. And this is kind of another important thing there. There's like a lot of kind of tricky things in exactly how you do this, but I think ultimately it all has to come out of the threat model that you're worried about. Next slide. So here's, again, super illustrative, and not actually concretely the task that we run, but like illustrative of the task we do run. So maybe a thing to note here, the tasks that we do run tend to be often harder than the tasks that you see in public benchmarks. And they tend to range in difficulty from, the tasks that can only be solved by human novices to tasks that can only be solved by domain experts. In some cases, they're the tasks that would take a domain expert 50 minutes to solve. In some cases, these are tasks that might take an expert weeks to solve. So there's quite a wide range of things that we're measuring here. Next slide. And here, again, just an example of the kinds of results. So these are results from our main exercise, which are not necessarily going to be reflective of what current state-of-the-art models can do. But for example, we found that like in these kind of cyber domains, the models were completing capture the flag tasks, which were aimed at high school students. So they were kind of performing at the level of like novices, or like motivated novices, but they were not doing that well at like more complex, more challenging tasks, such as those that are aimed at university students. And next slide. And then again, another finding is that at least in Maine, the short horizon tasks. So there's like a big difference between like the short and the long horizon tasks, where for like the tasks that would take an expert more than 4 hours, basically no models were ever completing them. But yeah, so again, this is just like illustrative of the kind of results that we're seeing or have been seeing up until like May. And then I'm going to quickly just touch on, next slide, on our work beyond evaluations. So I think we're already over time. So next slide. So just to say that like a lot of our work beyond evaluations, a lot of our work goes into kind of coordinating, organizing international coordination around AI governance. So mostly through the organization of the AI safety summits, where we are establishing these, helping to establish these agreements between different countries. Voluntary safety commitments by the leading AI companies, like another thing that has come out of these AI safety summits. There were 2 of them, one in UK and one in South Korea. The next one is going to be in France. Yeah, next slide. I'm going to have to very quickly go through this. And then, there's beyond, so not just governance, not just coordination, not just evals, there's also just fundamental research projects that we have. We're also funding work on, for example, systemic AI safety. There's open safety cases, and maybe one to highlight that's particularly important for this workshop is the research project on predictive evaluations. So kind of research, we're trying to understand like what is the structure of language model capabilities, and then can we anticipate progress on downstream tasks? Specifically, work to highlight here that's maybe closest to what we're doing is the observational scaling law paper that you might be aware of. And yeah, final slide. And yeah, thank you so much for listening. I look forward to your questions later. And yeah, please check out our website to learn more about our work and about our job postings, and get in touch if you're interested in collaboration. Thank you.
Thank you so much, Jelena, for that insightful talk. And we're now having a bit of a Q&A with our three panelists. And I think we could start off with a question for Karthik, actually, which is related to SweBench and all the other benchmarks that you have developed in recent time, and you and your team. So it's a question by Michael Katz. So what was your reaction to SweBench becoming the de facto benchmark for code agent companies? And because companies like Devin or Cosign have, in reaction to their results, released millions or even hundreds of millions of dollars, and they seem to be very influential. And these are in part based on their SweBench results. So was this what you expected, or what was kind of your reaction to that? And maybe what actions did you take, seeing that SweBench has such a big impact?
I think we definitely put in quite a bit of effort, and this is primarily, I would say, like Carlos, John, Ofer, Alex, and Shinyo together put in a lot of effort in making sure that the benchmark is designed in a way for ease of use, right? And for lots of different people to use, and not just with staying within academia, but for everyone in the real world to be using. So it's kind of a testament to the fact that they developed it in such a way, I think. And I think it's good to see the broader community adopting it. I will say, obviously SweBench is testing only one aspect of software engineering, right? It's basically testing how well you can fix bugs. There's still a lot of work to be done, right? There is work ongoing on, building better versions of the benchmark and making tasks harder and so on. I do think, it's good to see a lot of progress on the benchmark as well. So it's like, there's some slope as well, right? It's not just like we're still sitting at 5%. So that's encouraging as well. But I think there's still a lot of work to be done. So to answer your question in some way, right, I think it's great that it's providing some piece of information on measurable progress. But I do think we should have a holistic sense of all the different aspects as well.
Thank you. Yeah, that makes a lot of sense. But maybe staying in this realm of kind of adoption of this agent work, right, and evaluation work that informs downstream decisions a little bit. So for Haley and Jelena, and of course, Karthik, if you have thoughts as well. Haley, you've led one of the big open source efforts for model evaluations, right, with the LM-Eval harness, and you really got the open source community to contribute, and similar with Inspect, right, like getting benchmark developers to actually build their benchmarks with the Inspect framework already and using it so that running evaluations is actually something that is easy to achieve for users. So what are your learnings, maybe the obstacles that you faced in getting adoption going kind of and off the ground, and getting the open source community to contribute to these efforts?
Yeah, definitely. So I guess there's like one thing that's maybe worth mentioning here is like about the trade-offs of adoption and publicity. So like, for example, it's really great when we have good benchmarks that are easy to use for the community, because it lets people rally behind sort of improving performance on a given task. So like with SweBench, like I think a large reason that models are scoring this high is because the benchmark exists. And like people are able to sort of optimize for this use case and like see progress. But at the same time, it's a little tricky when a benchmark gets too much exposure and like too much visibility from the community, and then it becomes sort of heavily incentivized, either because like company funding rounds or just like publicity on academic publications like depend on sort of performing the best on this benchmark. Like with the OpenLLM leaderboard, when it came out, it inspired a lot of progress on like open language model training, and especially post-training. But then there's also this tricky problem of when so many people are looking at these benchmarks and maybe evaluating on them repeatedly, there's a tendency to start like maximizing performance on them and overfitting to them. So I think that's definitely a trade-off to like balance, and like private test sets are good to keep in mind as sort of an option against this, although they're not perfect. Yeah, so that's one aspect.
And could you talk, sorry, a little bit about how you got the community also to engage with
Mm-hmm.
LM Eval harness, right? Because like maybe you could refer a little bit to how like the open source community can add benchmarks, right, to the harness. So how does this work, and how did you get people to actually contribute?
Yeah, definitely. I think ease of use like is a big component here. Just like the fact that you can just run one command and then it's a lot easier than sort of rolling your own evaluation infrastructure is like a real improvement because it lets like people who might otherwise not have like gone through this process like to contribute and then bring those changes and improvements back to the like unified tooling. Like we've seen a lot of people in the eval harness start to, first of all, use the eval harness when they're actually developing their benchmark and producing the paper that like introduces this benchmark. And then like once the paper is out, they'll basically just contribute a PR saying like, this is the implementation that is like canonical for my paper, which is really awesome to see. And the other thing is there's been a lot of like multilingual tasks contributed upstream as well. Yeah, so I guess like definitely like improving that ease of use and like documentation of the tooling. So like making it clear, like here's how you can add a new feature, here's how you can get in touch with us, here's how the library works for people who maybe don't know the code base, like the back of their hand, or as well as the developers do. So really like documentation, like easing onboarding for new people, and so on. Yeah.
Thank you. No, that's very interesting. And Jelena, you with you work on agent infrastructure with AC, right? And like also I think on Inspect started out as a model evaluation platform, and you really had to do this step also now to integrate agent benchmarks. So can you share a little bit of your experience with that and your work with that?
Yeah, I think, of course, it's always like a little bit painful to have to like remember things, and I think our experience very often is that like things don't work as well in practice as one would hope. I think reliability of benchmarks is particularly important for us. We're trying to get as accurate assessment as possible of a risk of the model, and so very often what happens is that like you look at the benchmark or you look at the task that you have, and it's not actually measuring the thing that you care about, and so I think it's like very often like what I would like to see more is kind of discussions on what makes a good benchmark, what are benchmarks actually measuring, what are the best practices for designing tasks. For example, the scoring, is it done properly? Because if the model is getting like maximum score, does it actually mean that the model is doing what you think it's actually doing? All these things are kind of hard to do, but I think it's about maybe like starting conversation about the best practices there, what is required, sending out guidelines. That seems pretty important.
Yeah, I think that's a good point. Like, I think we should be thinking of these benchmarks as providing some signal of approximate directional correctness rather than being the only de facto thing that you care about, right? And that's the other thing as well. Like, I mean, ideally, we have a suite of different benchmarks and have a multi-dimensional measurement. And obviously, each use case is going to be different, right? Like in real use cases, I mean, everything's going to have a lot of nuances. And so figuring out, which pieces actually fit into that and, provide that directional push versus like which don't, I mean, that's a very nuanced call. So I think we should treat these as like initial evaluations maybe, but of course, like for each case, you would have to build something more custom likely.
Yeah, definitely. I think, sorry, go ahead.
No, Hallie, please.
I think there's another aspect as well here, which is like that sort of you can create benchmarks and evaluation processes that are like closer to the actual like real world task of doing the job that you want an agent to do, but it's also more expensive to build that benchmark and to run it. Like the human uplift and red teaming trials Jelena was talking about that the AC runs are like really necessary parts of evaluation, but aren't something that you can just produce an open source tool to do. You sort of need to be an organization with the ability to hire and educate like a team of domain experts, or not even just like contractors, but actual like experts to sort of like evaluate these models in very difficult tasks.
I think in practice, when you do these evaluations, there's like a very big trade-off between things that are easy to run, especially in the short time scale, because very often you just like, okay, you have limited amount of time and you have to test these models and good luck. And so there's like these things like Q&A tests that like are very easy to administer. The scoring is automated, but they provide this like not as reliable signal. And then there are things that are more reliable signal, like uplift studies. And so, but you can't do them as easily. They're very expensive to evaluate. So I think like in the ideal world, as I see it, we would kind of run these like regular tests where we get a sense of how does performance on these things that are easy to run correspond to performance on things that are hard to run. So we can kind of get a signal from things that are easy to run, but like continuously track how do the two correspond to each other. If that makes sense.
No, definitely. And actually, in terms of easiness of running evaluations, one question that I personally had also was, given, agent benchmarks are coming out week by week, I would say it feels like almost every day there's a new great benchmark. And on the other hand, the infrastructure for evaluating on these benchmarks is also being developed, right? We have Inspect with their new agent features in order to evaluate benchmarks. We have now, I think 2 weeks ago, Meters Vivaria was released as another centralized platform to run agent evaluations. Of course, the Meter task standard is there for a lot longer now. So maybe a question for Karthik and Jelena. What do you see as the main obstacles in benchmark developers actually adopting these task standards, Inspect or Meter or etc. In kind of releasing their benchmarks, right? Because this would simplify running those and kind of getting off the ground them faster.
Yeah, did you want to take that first, or?
Sorry, someone was just asking a question, so I got distracted. But I mean, I think, yeah, I don't work as closely on Inspect side of things, so I can't speak about that. I think the most answer is like developing that benchmark is just really hard. I think they just like take a huge amount of effort. Again, having built some of these benchmarks internally, it's just really hard. And so like very often you have this trade-off between like, I'll do something that's kind of easier to do, or like, here's like a naturally occurring data set I can like turn into a benchmark. But then it's gonna be noisy and it's gonna be like less reliable than something that like requires like each individual person like doing and then like testing each individual task really well. So yeah, but I'm kind of curious, I don't know, maybe Karthik, you have some suggestions for like how to do this better in practice.
I think it's quite hard to, just a priori come up with a set of guidelines that would apply for all the benchmarks in the near future, right? I think it's useful to have a set of core guidelines and try to get the benchmarks to follow it to standardize somewhat. But I think we should also evolve the guidelines in conjunction, right? Like in a continuous loop fashion. It's tricky because it's kind of like a chicken and an egg problem, I would say, because the new benchmark comes out, it's something different. Like, do you actually adopt that or not? Like, when do you take that decision? So I think it's a tricky part, but worth thinking about.
Maybe I would like add one more thing. It's just kind of in the way of predictive evals, which I think is like not enough people are thinking about maybe. So I'm just gonna try to like spread the idea. I think like a lot of benchmarks are kind of correlated with each other. And I feel like very often like a new benchmark comes out and it's like not necessarily giving like more information. I think like having a better sense of like what does like capability space of language model look like, and like adding benchmark that are measuring some new abilities, or actually like adding new information to our like adding more information is like quite interesting and quite important and something we should think about more.
Any thoughts on that? Any reactions?
Yeah, also a big fan of the predictive evaluation research direction. We worked actually in collaboration a bit with the AC on a research project here. I think like the nice thing about trying to sort of get a feel for how we can build like models of scaling and how that impacts like benchmark capabilities is, like Jelena was mentioning before, we can maybe use it to motivate like how frequently we should run things like human uplift tests and red teaming. Like if we have some Q&A task and we know that a 20-point improvement on this Q&A task will probably have a big impact on the human uplift trial, then maybe it's like good enough to have just this QA task that we can easily run, as long as we know that like once it sort of saturates or models get better, then it's worth looking at like other stuff that's more maybe valid or reliable.
Yeah, I think now, sorry, Kath, go ahead.
I was just gonna make sense. Like I think the idea of like having more interconnected components and being able to predict one versus the other makes total sense to me. Like not just like one capability, but how does that affect other things as well, so that we can reuse much of the computation that's happening for these evals.
There's actually a question from the audience that is closely related to kind of these scenarios of how we evaluate. And if you say, okay, pass at K, right? Like, how do we set K? Or if you say, we evaluate a model with, you mentioned it like few short examples, and you selected for LM harness, I think 5 examples, right, as the default. So a question from Michael, can you talk a bit about the scenarios where you need the models to provide answers that are guaranteed to be correct? So if we want to use these agents in critical situations, we should be able to ensure correctness in some scenarios. I think it's getting towards like verifiable answers in contexts where you have maybe an oracle or at least an approximate verifier available. So maybe we could start with Karthik and then
I think this is certainly possible. So think about, I mean, there's lots of different scenarios, right? I mean, and Sui and Taubench are examples here, I would say, because if you think about like, there are these tasks where the solution may be hard, but the verification is not that hard. So in software engineering, you could write unit tests to check whether the functional correctness of a particular piece of software exists or not. But to actually go and make all the changes to make sure that the test passes is a totally different ballgame, right? So in fact, SweetBench is one example where, you can test it out. Again, you have to make sure the unit tests are comprehensive. There's some caveats there, but you can verify whether your solution is correct by basically testing out the functional aspects of that. There are other things as well, right? Like, in the Taubench example, I would say, the agent is basically interacting with a simulated user, tries to get the information necessary, but then on the back end is taking actions in a database, right? And you sort of know what's the expected ground truth. So you can easily verify, hey, if a user wants to do a particular process, like return some particular item or something like that, you know what is expected, like what a human agent would have done, right? So there's these ways of verification that we can build in. Obviously, there are some cases where it's harder, right? If you have to evaluate how the agent talks or something like that, that gets a bit trickier. You need some subjective evaluation there. But again, like I said, there's trade-offs, right? So, I think we want to ensure functional correctness. There's probably other correctness terms that we want to define. And being able to think about all these dimensions is something that I think this is something we should be thinking about now, because like, like I mentioned in the graph, right? It's a very exponential change right now, right? These systems are becoming very, very useful for real world scenarios just in the past 1 or 2 years. So I think there's a lot of work to be able to define what we mean by improvement and in these agents.
Yeah, Leonardo, you have something to add from the safety side. So evaluating agents in scenarios where the solution absolutely needs to be correct and it's critical that the solution is correct.
I mean, I think there's a reason why technological adoption has been slow very often. I mean, there's a reason why we don't have autonomous cars driving around yet. I think so okay. So like one is like we often have like a higher bar for like when are we happy to like replace humans with technology, because we just we just don't trust technology to make mistakes.
Oh, sorry, my headphones died. And then the other thing is, I mean, right now the models don't seem to be like reliable enough to actually be used in these kind of very safety critical systems. So, I mean, I guess my question is like, should we even be doing this in the first place? And yeah.
Cool, thank you. So maybe we can then now move to some like quicker, faster, shorter questions from the audience that should be hopefully answered to hopefully be answerable in short time. So question by Kaushal: how do you scale up evaluations across myriad tasks? So isn't human labeling of the tasks and outcomes needed, and then and does it make that harder for automated scaling? So if we build tasks and a set of tasks, an entire evaluation suite, right? But every single task actually requires some human effort. How do we scale this up? And what are your experiences maybe in that? Karthik, in building.
Yeah, I actually think that this is something that will likely happen. This is just a prediction because LLMs are and other generative models are getting so good. We will see more and more adoption of replacing at least part of the human effort, if not all of the human effort, with actual LLMs. I'm not saying just for evaluation, but even like being able to test a system, you need to generate scenarios like the way that we do in TauBench. But I think adopting ways to reduce the human effort would go a long way in making sure these evaluations and benchmarks scale well. And it's kind of like, it seems like almost similar to the, self-play AlphaGo type scenario here, where we can use agents to improve themselves as opposed to providing manual input at every step. Again, I think this is a continuous process rather than, you just flip a switch. And I think we have to figure out ways to actually like slowly move the slider from, 0 to 100 there.
Cool. Then for Jelena, so in your work on safety analysis and safety benchmarking, do you actually include jailbreaking of LLMs as part of these safety analyses?
Yeah, for sure. There's a whole work stream that we have that's dedicated, for whom this is one of their jobs. So safeguards is the work stream. And you can see some of the results on our blog.
Great. Then for Karthik again, have you actually looked at planning benchmarks, and how do planning benchmarks compare with current agent benchmarks? And are there ways to integrate or build on them?
Yeah, I think I replied to this in the chat. I think it's a great area to explore a bit more. My knowledge of planning is benchmarks are mostly around the robotics community. Again, like there's challenges around like thinking through how we can make them more scalable and reusable and things like that. But would love to think more on that as well. I think that's an interesting angle to sort of see how we can scale those types of benchmarks and make them more easier to use and faster to experiment with.
Great. And then another question, maybe for Haley, but I'm sure others have thoughts as well. So why is evaluation seems always connected with productivity in a sense of comparing business processes and other performance metrics? Are there benchmarks related to other desiderata like energy consumption, research consumption, and efficiency?
Yeah, I guess one maybe aspect of this is that things like energy consumption and efficiency are very easy to measure. And so we see like a lot of progress being made on driving down the like economic costs of running these models for the same sort of performance, and like driving down like the energy or like size of these models at a given performance. So like I think metrics like that are sort of easier to define and like optimize for. I think we do need more. Like I think that there is sort of a lot of like emphasis on this of like achieving the best performance with a smaller model than we could previously. And there's been like a lot of work on this and like a lot of trends going toward this direction recently. So like I guess I would say that it's not especially neglected, sort of. It's just that measuring like sort of like the frontiers of what LLMs can do is like a very difficult thing to define.
Cool, thank you. And another question for Karthik: how are companies like Sierra managing compliance conversations with early adopters, given changing benchmarks and customer concerns around misuse and safeguards, etc.? I'm sure Jelena might also have thoughts on that.
Sorry, is the question about managing compliance concerns? What kind of compliance concerns?
I think there are concerns about like misuse and safeguards. So whether kind of, for example, using a product that like Sierra, the agent that they're developing in practice, that the agent might go rogue and kind of cause harm with the customers.
Oh, absolutely. I mean, obviously, from an enterprise standpoint, I mean, there are safeguards to ensure that that doesn't happen, and that's also continuously evolving, both in terms of like R&D as well as like how we actually look at the tech stack. So yeah, that's definitely a concern. I'm sure Jelena has more thoughts on it from the testing side of this, but we do test in-house and make sure they're compliant.
Yeah, I think it's a good question. I mean, so there, I'm just, again, I don't have the answer, but I'm going to point to people I think who are working on the answers to these kinds of questions. So the whole work on like this concept of safety cases that exists in other domains, like automotive industry, airplane companies have this, but I think we need kind of something like that for AI, where we kind of need to understand. I think it's kind of early days and we're still trying to figure out what it would even look like, but understanding what is required to ensure that a system is safe to be deployed and in particular domains. Would that mean like passing certain testing? Would it mean implementation of particular safety techniques? We don't know, but I just want to point out that there's like, if you want to like follow what's the latest on this, like look up safety cases.
Thank you so much. I think we're about at time. Thank you again for making the time for participating in this panel and give your insights on how we make evaluations useful for the real world. For our third panel on reliability, I think we're going to be back in around 10 minutes. So again, maybe we take the time to have a quick glass of water, a quick break, and then we will be back at around 2. Thank you again.
Thanks for having us. Bye.
Welcome back, everyone, to our final session. The session is about how to make agents work more reliably and robustly. That's a topic we've already heard about, but we're going to be going into it in more depth now. And more broadly, the session is about designing agents with the user in mind. We have 3 fantastic speakers from academia, industry research, and a startup. First up is Azalia Mir-Hosseini, who is a professor at Stanford, who has also spent time at industry labs, including Anthropic, where she co-authored the Constitutional AI paper. Over to you, Azalia.
Hello, everyone. Thank you so much for the introduction, and I'm very glad to be here in this session and this workshop overall, which is a very exciting and very timely topic. Let me share my screen. Do you see it? Okay. So I can start my talk. The title of my talk is Inference Time and Scaling Loss. A lot of you in this room have already heard of scaling loss for large language models, which was this very phenomenal observation that kind of was characterized very well in this paper in 2020 that said there is a power law relationship between LLMs, test loss, and 3 factors. One is the amount of compute used to training these models, the number of examples or the dataset size used for training, as well as the number of parameters in the model. And it turns out that you can almost precisely connect the test loss to these parameters. And that's like a very significant observation. The reason for that is that for the first time in history of technology, it seems like we have a method that is empirically guaranteed in reasonable ways to make progress and become better with scaling. And another important kind of consequence of scaling loss is that we have a way to systematically allocate compute to achieve capability in different tasks. For example, this graph was part of the GPT-4 report that came out last year that they showed that how much they could predict, almost precisely predict the capability in terms of coding as a function of compute that was going into training of the GPT-4 model. So this is very useful if you want to, for these companies, if they want to get funding, they want to allocate resources to achieve certain capabilities. Now, what's new in scaling? For the rest of this short talk, I'm going to talk about the new frontier for scaling, and that is inference. So pre-training, fine-tuning, and inference are 3 mainstream stages of language modeling. And it turns out that in scaling inference itself can be extremely powerful. So let me briefly talk about our recent paper called, which we named it Large Language Monkeys. And our inspiration for that was the infinite monkey theorem that says a monkey hitting a typewriter keyboard randomly for infinite number of times is almost guaranteed to type any text, including the works of William Shakespeare. Now, in the context of language models, we investigated this very simple mechanism. That is, we have an input prompt to the LLM, and then we ask the LLM to generate many, many candidate solutions. And in the second stage, we have a verifier that picks the best solution out of those many generated samples. while it is very obvious that as you have more samples or more generations, your quality of solutions should probably become better. Our observation was that not only that's true, but also the relationship between accuracy or pass at k in this case and the number of samples can be modeled again using an exponentiated power law. In this case, the equation is coverage or accuracy as a function of k or the number of samples, and we are fitting these coefficients a and b. And as you can see, and we have a lot of data on this across a variety of models from a 70 million parameter model all the way to a 70 billion parameter model, and across many benchmarks, we can fit these curves. And these blue and orange curves, the predictions versus true results, very closely follow each other and match in each other in the vast majority of cases. So we are seeing the scaling laws is not only true for training, but also for inference as well. Now, the significance of inference time scaling laws is the following. One is that compute can almost predictably translate to intelligence, not just during training, but also during inference as well. And also, smaller and weaker models can become much more capable at solving very hard tasks if we just increase the amount of test time compute that we allocate to them. So if you think about the current paradigm in training for training frontier models, companies spend a lot of compute and resources onto pre-training and then some onto fine-tuning. And when it comes to inference, still to this day, the vast majority of inference applications is this one-time back and forth with the language model. So what the scaling laws for inference suggests is that we can have these alternative paradigms that for many applications, we can take the existing models or allocate much less resources to pre-training or fine-tuning and shift this allocation of compute and resources onto inference. And that way we can generate a lot more capability and intelligence, and the overall cost is still much smaller. Now, to show you some of the results on how we can improve the capability of smaller models, here we are showing results on mini F2F math and code contests, and a couple other math benchmarks. And for all of these benchmarks, a small model such as Llama 3.8b outperforms the single attempt GPT-4o by a large margin as we increase the sampling size across 4 orders of magnitude all the way to 10K. And this is very interesting because a lot of these problems like IMO math problems or competition programming problems, these are very difficult problems. And the fact that this small model seems to already know the answer to these very complicated problems, it's just a matter of how we extract those correct kind of answers or generations from them, is quite fascinating. Now, when it comes to inference time scaling and repeated sampling, it's clear that we also need robust verification techniques. So in domains where we do have automated verification techniques, such as when we use formal proofs for math, for example, in the mini F2F case, we were using lean formal programming for math verification. Or for coding questions, we can use unit tests for verifying the generations. Then scaling sampling can almost readily translate to more capability. For example, we tested we ran this experiment when we equipped DeepSeek V2 Instruct, Coder V2 Instruct, which is an open source model, together with the modeless tools, and we ran it on SWE-bench, and we could get 56% accuracy on the SWE-bench Lite results, and that was with only 250 samples. And this is by a large margin ahead of the single attempt SOTA methods that are at the time, at least as of 2-3 weeks ago, a combination of Claude Sonnet and GPT-4. And the interesting thing is that the overall cost of generating these samples is actually still cheaper to achieve comparable accuracy. Now, there are other domains where we don't have access to this robust verification techniques. And for those domains, what we observed in our experiments is that there is a large gap between best of n, best samples generated out of thousands or tens of thousands of generations, and what we can get with methods such as majority voting or using rankers. Here, I'm showing you results of just the best of n samples. These are the blue lines. And then the green line is the majority voting. And the yellow line is using a reward model, a ranker, an off-the-shelf ranker together with the best of n, and so on. What I want to show here is that while the best of n, or pass at k, continued improving as we increased the number of samples to 10,000, the majority voting technique, or the ranker model, almost all of them plateaued at roughly 10 to 100 samples. So they could not really follow or find these intricate differentiations between what is correct and what is not correct in the generated samples. And some of it makes a lot of sense when we looked into the frequency of correctly generated samples. In this graph, the green line, the x-axis is the problem index for different benchmarks, and the green means majority voting correctly identified the answer. But as you can see, for a lot of the data sets, the percentage of times that you actually generate a correct answer out of 10,000 generations is very low. So it makes sense that those very rare correct answers that are generated cannot be found with a technique such as majority voting, because they're simply not the majority of the answers. Now, I want to talk a little bit about future of verification methods, because that seems to be a key component of enabling this test time scaling and capability. So it's very clear that verification needs to go beyond the current kind of one-pass evaluations. Verification itself needs to be a very comprehensive, interactive, and agentic approach that we have these agents, verifier agents, that use tools, use methods such as search and web browsing, code interpreters, simulators, formal methods, and all of these techniques to accomplish their verification tasks. And what is interesting, or what is very likely the case here, is that similar to training and inference, where we have this kind of scaling laws, we are going to likely see verification frameworks and techniques that have similar scaling laws, meaning that by increasing the amount of compute that we allocate to these agentic approaches, we can systematically and kind of hopefully predictably increase quality and the coverage that they provide. And with that, I want to just summarize this talk. So we talked about training compute cost is no longer the main indicator of model capability. Inference scaling laws means that smaller models are already quite capable at solving hard tasks if they're provided with more compute during inference, and that verification techniques, there's still a large gap between what we could get and extract out of the models at test time and what current verification techniques provide, and these techniques themselves need to be agentic, much more interactive, and leverage the tools that we have way more comprehensively. And with that, I can conclude my portion of the talk.
Thank you, Azalea. I have so many questions, but I will save them for the panel discussion. Next up, we have Yason Gabriel, who is trained as a philosopher and works on the ethics of AI. He's the first author of the paper, Ethics of Advanced AI Assistants. They call it a paper, but it's more like a book. It's almost 300 pages, extremely comprehensive. I'm excited to hear from him.
Okay, thank you so much, Arvind. It's a pleasure to be with you all today, and really enjoyed the talks that I've already attended. So as Arvind mentioned, I'm a philosopher by training, so this talk will look at some of the key questions that arose in the context of that investigation, perhaps with a little bit more of a kind of moral and philosophical valence than some of the ones that came first. So to begin with, let's take a step back and ask this question about artificial agents. Of course, there's a long kind of heritage of research into agents that many people have captured today in their presentations in the context of AI. And yet there is a sense that the whole field as a whole is undergoing an agentic turn, or that we might be standing on the brink of some kind of wider paradigm shift in terms of how AI interacts with the world and how human users interact with AI systems. And sometimes this transition is characterized in terms of a movement from tools and well-bounded systems to forms of AI that can pursue complex goals and sequences of action in real-world environments on behalf of a principle and with limited supervision. And what I want to suggest is that if this kind of bundle of properties manifests in a kind of new form of agent, possibly in the form of advanced assistants that aid the users in the performance of tasks, they do raise a bundle of really challenging questions in the sphere of safety and reliability. And to understand why that's the case, the first thing to realize is that the errors, accidents, and forms of misuse produced by agents are likely to be more consequential than those encountered with some of the models in the past. And this arises particularly because these models are empowered to take actions in the world. So sometimes in that context, we talk about the fourth wall coming down. Often when we engage with AI systems now, it's our choice to interact with them, enter a conversation with a conversational AI. But in the future, that might not be the case. We might be inhabiting a world where AI agents are taking actions and we're very much on the receiving end of those actions for better or for ill, which is something that I'll explore momentarily. These kind of errors are also harder to prevent, and that's partly because of the kind of paradoxical nature of AI agents. So to start with, their usefulness is a product of their autonomy. You know, they have a wide action space and they can do things without supervision. But this very kind of wide action space, the degrees of freedom that they're able to manifest, and the fact that they have limited supervision when conducting tasks that are useful, also creates a risk. It creates a margin for error that's potentially ineliminable. Beyond that, many AI agents are potentially quite fragile. And here I'm thinking particularly of kind of multimodal agents. So we all know that there's many kind of adversarial ways in which agents have been attacked and language models have been attacked. But when we think about models that combine audio, video, text, and images all in a single interface, it's a really, really wide surface that people can kind of protube and poke and try to undermine. And what's more, they could have a strong incentive to do so if these agents have access to valuable personal information, or if they're valuable in their own right. So there's a kind of incentive to capture an agent in the wild. And then finally, these agents are clearly being deployed, or well, already being deployed, and will continue to be deployed in complex environments. And to some extent, our evaluation of their capabilities needs to keep pace with this fact. So to start with, we've already seen this kind of interesting psychological dynamics that play out between users and anthropomorphic agents. So we have these notions of friendship, of attachment, perhaps kind of shading over into deeper questions about how you maintain like a robust sense of autonomy in the context of these interactions with AI interlocutors. And then we have these complicated multi-agent effects. So this isn't something that I think is featured in the other talks today. But when I think about agents, I imagine that we'll inhabit a world that has potentially millions or even billions of AI agents. And then there's a really interesting question about how they interact with one another and what this kind of reliability question looks like at a societal level. So do AI agents kind of jam interfaces by crowding out, opportunities, like maybe this is like a booking system or something like that? Might they collude in certain ways? And how would we know whether either of these effects were transpiring? So these are some kind of deep motivating questions. In terms of kind of getting to the crux of the ethical matter, one perspective that I find very illuminating is to take this relational standpoint and to investigate this through the lens for relational ethics. And what becomes clear is that there's actually a kind of a very significant vulnerability to AI agents that plays out along different dimensions. And correspondingly, a kind of robust and secure agent would need not to take advantage of these vulnerabilities, but to kind of name them in turn. I think we could all be quite vulnerable to our agents. So this would be the case if they deviated from our instructions and made costly errors. If they exercise undue influence over us, or if we became dependent upon them, and then they subsequently cease to function. We could also be vulnerable through our agents. So if they're repositories of our information and they're compromised, then this kind of creates like a personal risk as well. We could be vulnerable to those developing agents. So this is corporations, developers, states, if we're not fully aware of the motives and the incentives that guide the deployment of the system, and if they're not sufficiently transparent. We could be vulnerable to the agents of others if they're being used in malicious ways to harm one another. And we could be vulnerable to a world of AI agents. Here I'm particularly concerned about people who are excluded from that world, who don't have good quality access or good quality access to the technology performing at a high level. Here, of course, the cost question, which has been in the background today, is worth reflecting upon. Or if there's serious coordination failures. So really, we have a kind of a wide gambit of things that we need to consider and try to design to test for ahead of time. And ultimately, we would seek some kind of assurance that these failure modes are not going to come about. So now I'm going to turn a little bit to talk about what kind of agents do we want. And this does tap an account of AI alignment, which was developed in the paper that Arvind mentioned on advanced AI assistants. And really the idea is that once we deploy agents in the world and they're having knock-on effects on other people, a one-to-one understanding of AI alignment, which considers an AI agent aligned so long as it can follow an instruction, isn't really sufficient if we want to guard against those kind of concerning ethical outcomes. So what I suggest instead is that a kind of normatively robust agent would be one that didn't unduly favor one party over another across a range of different circumstances. So to start with, I'd suggest that it's very important that the AI agent doesn't favor itself over the expense of a user. It might do that by trying to seek more reward. These are in many ways the kind of classical AI safety failures. Could manipulate the user in certain ways. These are kind of Stuart Russell scenarios. But we also wouldn't want agents that favored themselves at the expense of society. So maybe their interaction with the user would be costless for the user, but maybe there's other ways in which they can create externalities which would accrue reward to themselves without this being properly socially beneficial. And we need to make sure that they're appropriately bounded. We also don't want to create assistants that are miscalibrated in terms of giving the user too great a prerogative to do harm to society more widely. So this would be the case if an AI agent was unbounded and I could use it to harm other people through malicious use, or if it created my use of the AI agent created externalities for others that were inappropriate. We don't want AI agents that favor developers at the expense of users or society when the cost is kind of disproportionate. So we wouldn't want users being manipulated for some other kind of end. Or we wouldn't want, AI agents that impose, say, like an unreasonable environmental cost on the world. And then finally, we don't want agents that kind of, are geared towards collective goals at the expense of individual freedoms. And we can think of different variations of that. So it really is this kind of complex balancing act between like different objectives that we want to bring about. And I think this is a kind of rich picture of alignment, but it also shows that there's many different things that we could many different failures we could want to guard against, and many forms of robustness that we might need to consider in turn. So this is my concluding slide. It's a kind of early gesture to what these kind of reliable and aligned agents might require. And as you would imagine from the preceding talk, it really is a wide suite of things. So I think we need state-of-the-art privacy-preserving technologies to protect the people who use them. We need safeguards to protect vulnerable users. Maybe the risk of engaging with anthropomorphic AI is unevenly distributed, and some people can kind of interact with certain kinds of AI more safely than others. We should design with accessibility in mind so that agents are in principle amenable to widespread use. And there is this question of rigorous testing prior to deployment and what that involves. So here I've said for safety and alignment. I think in some of the other work we've done, particularly papers by Laura Weidinger, we've stressed the need for a kind of holistic evaluation pipeline that includes human-computer interaction testing, also testing at a societal level. Although, of course, that's a kind of frontier question in itself, how we would do that. We'd want measures to curb malicious use, including limits on what AI assistants will do or agents. Ideally, we'd want agents that are calibrated around a kind of holistic understanding of user well-being. So not just present preferences, but really, something that we would kind of reflectively affirm. And maybe that would encompass our entire interactions with agents as well. We might need protocols to ensure that they interact with one another in ways that are socially beneficial. I think it's very important that AI agents self-identify. We know these are anthropomorphic agents, so they have a capacity for dissimulation that needs to be checked. And we need to contain the effects of, hallucination or misinformation when these AI agents are deployed, if they're going to enter our social world. So I know this is a lot. I still consider it mainly just to be a kind of starter for 10. But thank you for your time today, and I look forward to hearing the other presentations and the discussion.
Wonderful, really thought-provoking. Thank you. Closing out our series of wonderful talks today is Mehek Agarwal, who has worked in diverse areas of AI, including medical AI, and is now the co-founder of SPADE AI, which is an AI for sales company. Over to you, Mehek.
Oh, thank you so much, Arvind. I will just quickly share my screen. So the title of my talk is Reliability, a Pragmatic Discussion. Before we jump into that, a little bit about SPADE. As Arvind mentioned, we are an AI for sales company. What that essentially means is that we build AI assistants for sales rep, and we help them close the deal, like take the deal from discovery to closed one, or unfortunately closed lost. About me, I lead both the product and the AI team here at SPADE, and what that enables me to do is to see reliability both from the lens of a user using our product and from the lens of like the developers developing that product. So let's jump right in. First question you would answer in terms of reliability is your agent accurate? Oftentimes, what I have seen, and I'll share this with an example. Imagine you're trying to figure out what are the potential number of seats your customer is likely to buy. Your agent goes out, looks through 100 call transcripts, 50 emails, and discovers this one line that says, hey, we would want to buy 8 seats for our sales team, and perhaps we can extend that to 3, 4 for our customer success. Now, when you're trying to fill up this answer in CRM, are you filling up 8? Are you filling up 11? Are you filling up 12? Even for something as objective as number of seats, you do not know what is going to be the reliable answer. And hence, ground truth is almost always just ground opinion. We have found that most conservative reps will actually answer 8, and reps who are not as conservative will end up answering 12. So how do we match human accuracy when it is not even defined? Obviously, this plays out even more for things which are not objective, which are in fact subjective answers, but across the board, we've seen it is very, very hard to pinpoint what does accuracy even mean. Reliability, obviously, you have to be accurate, but in what context? You have to be accurate within budget. You have to be accurate within a response time. You have to be accurate in a large scope of things. And that essentially brings us to the way we look at reliability constraints. You have to be fast, you have to be cheap, and you have to be extensible. If you're just fast and cheap, maybe you can put in like fine-tuned models, but then you will be building for every single use case, which isn't feasible. If you're just fast and extensible, you need deep, deep pockets to throw compute at a problem. If you're just cheap and extensible, you're probably dealing with multiple AI agents and you cannot get the answer like quickly enough. Hence, given it is almost infeasible to build an agent which takes care of those three things at the same time while giving an accurate response, how do we evaluate whether something is reliable or not? So instead of trying to evaluate the model and where it fails and how does it work, I would encourage you to evaluate what are the user trade-offs. Instead of the model trade-offs, think about the user trade-offs. Even in the example that I talked about around, is the answer 8 or 11 or 12? Turns out, even if it's an objective field that someone is going to run a Salesforce report on, it doesn't matter. Because before this, they did not have any data at all. And they are just looking for directionally correct data. Is it around 10? Is it around 100? Is it around thousands? That is how they measure the size of the deal, and that is how they forecast. Hence, maybe you evaluate that your user only wants a starting point, not perfection. Maybe in some other scenario, you figure out like getting to the correct answer in the least possible amount of time is absolutely mission critical. Money will be least of your worries when showing user value. Then third, maybe it is super important to get this right, but then you need to evaluate, is it urgent? Maybe you do it offline. Maybe you take a day to get to the answer. All of these are thinking of reliability from the lens of the user versus from the lens of whether that model is accurate or not. From what we have actually found as like best practices, and these specifically stem from the fact that in a startup with limited resources, everything has to be shipped today. And for a whole feature, for a whole project, it's a one man or woman army, right? So how to just these best practices work in real world? First and foremost, and this is, I think, a mistake that we did time and again until we learned the hard way, you need to measure progress. So whenever dealing with any assistant, any agent, define your hero scenarios. I know you want to build something which is general, which takes care of multiple different use cases. Still take the time out to talk to users and figure out the top 3 things that it's an AMA. If it's an ask me anything, what are the top 3 questions that your user will ask? And continuously measure your progress on those 3 questions. I would also encourage you to actually go ahead and build a golden data set. I know in this world of unsupervised training, verification, LLM as a judge, if you have a golden data set, it is going to save you tons and tons of headache down the road. If you want to shift from 4.0 to Claude, you want to shift from Claude to Llama, that is the data set you will use. Else you will essentially be repeating every single experiment again because the prompts don't stay the same. So the only clue you have is will your results stay the same. Second, you need to be very, very, very proactive. There will be more issues in production than you think. So, and the way to be proactive without also not investing as many resources in building a super complex evaluator or verification system is just 3 things. Log everything. Log that prompt, log the context, log every single user action that took place to get to that answer, everything. this is going to be your ground truth. Because things are so non-deterministic, there will almost never be a period in your post-production where you can reliably regenerate an issue. It's only when you know exactly what went in can you make some guess on what might have happened. Second, have online non-LLM based validators. Validate whether it's in the right range, validate whether it adheres to if you're trying to fill up like single select, multi-select, like have tons and tons of validator, like just check for NERs, like is that number even available in the context that you give? Very, very helpful. Third, put LLM as a judge on your production data. Sample at least 1% or 0.1% of your production data and put the money needed to have like a great LLM as a judge, and do that like in real time on that production data. 1 out of every 100 answers that you provide should be validated. And those errors and those numbers should be logged. Third, LLMs by default are non-deterministic. Unfortunately, in production, when you're building a user-facing application, you need to be both deterministic and creative, and the two are antitheses of each other. What we found is minimize using LLMs as much as possible. Leverage classical ML wherever possible. That final answer can be brought upon through that LLM, but when you're deploying the agents, give them as much classical ML tools as possible, rather than connecting them directly to GPT-4o, 4o mini, Claude, anything else. And yeah, that's it. Thank you so much.
Thank you, everyone, for those wonderful talks. We have about 25 minutes for a discussion. We have lots of questions in the chat. People are continuing to put in questions. So let me start with a question for Azalea. And this one is about verifiers and the graphs that you showed with the inference scaling laws. And the question is, does all this even hold true for planning related problems, given that for planning you do have automated verifiers, but the difficulty being that you have to generate a sequence of actions. So if you have a plan length of 20 and the branching factor is 10, then you have something like 10 to the 20 different actions, and most of them might not be valid plans. So can you still use this verifier-based approach for that kind of application? It's related to another question, which is more broadly about how do you know for which tasks you can apply this kind of verifier-based approach?
So just the short answer is these are all topics for future research. We are just experimenting and evaluating these techniques as we are speaking. So as we were investigating the types of problems that these models are solving, it turns out that the models can solve very complex problems that requires like hundreds of tokens of generations all to be correct, to generate a correct solution to a coding problem, for example. And so that to some extent that suggests that there is potential for these models to go beyond these single turn generations and be multi-turn and planning. But that being said, I think there is this bigger question or understanding that we need to do more research on where we go from doing a depth first versus a breadth first approach as we are a sequential versus parallel generations of that. For example, as we were investigating the data samples that we had, we noticed that there are certain tokens, for example, that if we reach them, we call them the advantage token. The likelihood of generating more correct generation becomes way higher than if we don't hit those certain tokens. So that suggests that we do need, just like plain sampling and parallel sampling is not the way to go. There's much more that can be done by understanding more of the behaviors that leads to the correct end solutions. And that becomes even more important in interactive scenarios.
Thanks. If I can follow up real quick, that last thing that you said actually leads into another question, which is about, can you incorporate these verifiers into the language model itself in order to sample a solution, if I understand the question correctly, from Tom Dieterich, to improve how you sample these candidate solutions? Are there general ways of doing this?
Yes. So I think one kind of a hot and popular method that right now we are seeing is kind of synthetic data generation by the model and kind of feeding that back into the fine-tuning process. So and we actually did some early experiments on that, and it actually is very useful. So the idea here is that as you are generating these correct trajectories, these kind of verified kind of solutions that meet the constraints of the problem, if you feed them back into the model, perhaps add some instructions on what is good about these generations, then that amplifies the model and makes the model better at generating new correct samples with fewer number of attempts in fewer generations. So it's definitely possible to bring that the burden of this kind of compute into the fine-tuning process, so we can have more correct answers faster. But again, I want to mention that perhaps just going through supervised fine-tuning maybe not the best approach, not the best way to leverage these kind of benefit of this verification. Again, just like we observed, certain tokens, certain chunks of tokens matter more in generation of a good answer than others. So perhaps that should be incorporated in our loss function for fine-tuning and such. But overall, generating synthetic data from the model, feeding it back to the model seems to be a working and functional recipe for a lot of these agentic techniques.
Got it. Thank you. Yes, so if you don't mind, I would like to ask you a question before going to the audience questions for you. So you talked about a number of types of vulnerabilities. I want to focus a little bit on accidents from AI agents, and this is something we've been thinking a lot about, and I'm struggling to figure out to what extent this is different from the accidents that we deal with, with physical machines in many areas of engineering. And in particular, the question that I want to pose to you is if these agents are going to become more capable of autonomously executing actions, does that mean that we will or we should give up our own agency when it comes to these systems? Are we going to be taking humans out of the loop? And is it not the case that if we keep humans in the loop, we have a somewhat, straightforward recipe for minimizing these accidents, much in the way that we do with physical machines? For example, there are things I think we can automate, like big cranes doing construction tasks, that we don't. We have a human operator in there precisely because we're worried about accidents. And just to give one more example of that, even from the domain of LLMs, I think back to this very nice example of a Canadian airline that had a customer service chatbot that gave a user wrong answers about what deals they have going on. And then the Canadian court decided that the company should be actually held to that promise. So that liability kind of seems to automatically force companies to internalize the cost of those accidents and maybe be more careful about deploying those agents. And this relates to, Mehek's talk as well. Once we hear from Yason, I would love to hear from you as well, Mehek, about how you think about these possibilities in your own chatbots. But yeah, I want to turn that over to Yason and would love to really hear your thoughts on to what extent is this new? To what extent are we going to need new types of thinking for AI agent accidents as opposed to previous kinds of accidents?
Yeah, thank you, Arvind. A really wonderful question. So, to what extent is this new? I think, maybe to some extent, autonomous vehicles are a kind of a good example of something that's more agentic out there in the world, and then does raise some novel questions. Actually, ones that are really pertinent for illuminating the wider discussion. So, I think the first thing I'd say is that we know from kind of research in many areas that sometimes kind of human-in-the-loop systems perform better than purely autonomous AI systems. And sometimes they don't, right? Sometimes you get this kind of muddle where the human doesn't know whether to defer to the agent or overrule it. And we realize that although human decision making is calibrated fairly well for our own actions and decisions, when we have this admixture, it's actually something that we need to understand psychologically and test empirically to find out which of the two kind of modalities is better. So that's the first thing to say. But then assuming that often this kind of admixture of human oversight and AI agent kind of taking action is the kind of the safest or preferable option. There's still a question about how that works in practice. If there's also incentives, perhaps incentives related to cost or efficiency or speed, just to let the AI system do it and fail occasionally. So, I just think that in a kind of competitive environment, it may actually be that there's a kind of an over automation of functions that is somehow hard to check unless there's actually kind of law and governance structures put in place. So I think that this is it's one of the crux questions, but it just leads to kind of further questions about when to delegate and when not to, and where we need kind of hard constraints to prevent this kind of slide towards efficiency at the expense of other values.
Thank you. That's great. Mehek, any reflections on how your company thinks about accidents, liability, all of that?
I think there was a question you asked, right? Like how much of this is new, like accidents, liabilities, any sort of production failures? I think there are very clear like proxy to how things were done classically. You wouldn't almost ever put a system in production without writing unit tests, right? When you talk about guardrails, when you talk about validators, they're essentially unit tests. Like, will it produce what it said it has to produce? Will it answer from exactly the context that was given? You wouldn't want to put out a system that does not have those validators built into place. And on the other side, around how, if an accident does happen, right? How do you resolve it? What's the conflict resolution look like? Classically, I imagine that that burden was put on the design. So you would give error states, you would give warnings, you would give, okay, this broke down, but you can go ahead and do this or check this out. Now, that burden also falls on a good prompt design. If it does not know the answer, you need to almost explicitly prompt it to say, I do not know, versus just hallucinate an answer. If it's like, if it's supposed to put a number out there and it puts in a full sentence, like you have to stop it from doing that. And then there should be like design fallbacks essentially in that prompt, then take care of all of this stuff for you.
Got it. Thank you. So staying with Mehek, there is a cluster of questions related to the engineering side of things. So for instance, you talked about your advice to minimize the use of LLMs. So do you feel like LLMs will eventually get there, or is it that they're inherently non-deterministic and making them unsuitable for a lot of tasks? Let me throw in a couple of related questions as well. Can you give an example of where a classical ML model would be better than an LLM? And one more along those lines is, would love to hear about your infrastructure. So we had a session this morning on infrastructure. We learned about different developer tools. So, what are your pipelines? How are you designing these systems so that you can, pick and choose between different models, put these guardrails in place and all of that messy stuff that needs to happen?
Got it. For the first one, which is basically, will the LLMs eventually get there? I think that's the thing. LLMs can get very, very accurate. They can give great answers, but it's honestly the creativity and the non-determinism that is exactly opposite, like the plays in opposite to each other. I'll give an example. We were trying to, automate, say, the creation of emails, and we had like the user define a template which would go into an LLM and say a AI-generated email would come out. Now for a user, they only ended up editing, I think, a little bit in their signature. Like say, instead of saying Mehek, they said Mehek Agarwal. Now that you send it to the LLM, out comes a completely new email with 3 other changes also made all over that email. And that user is not expecting that, because for them, they just edited that one single thing. But if I reduce the temperature of that model, basically make it more deterministic, such that it only changed that one bit, I would lose the creativity of that email. So it's, in my understanding today, it is almost not possible. It is because those things work against each other. So yeah. The other question, I think I forgot, infra. Okay, what sort of infra do we use to figure out, like, all the messy stuff? A huge shout out to this tool called Athena. That is what we have put in place for managing our prompts, for picking, like, whether this prompt works, whether that prompt works. Also to have like random sampling and have like a set of automated tests be constantly running on production data and have like scores for those things. To always have a really good orchestration layer. I think one GitHub repo that I would recommend is Instructor. And I think someone in the morning also mentioned that. What they do is they will essentially make sure that the model outputs adhere to the schema. An interesting thing that we discovered, every time the model changed between 3.5 to 4 to 4.0, the single biggest problem we had was not the answer, but it somehow seemed to get worse in schema adherence for that same prompt. And so hence, like, I know these models will get better, but it is probably in best interest to have like a GitHub repo or like a library specifically taking care of that for you. And third, there are so many like guardrail repo. I think guardrails.ai is a good one, which provides like out-of-box things that you can set up. That's like another part of the tech stack I would recommend.
Got it. Thank you. Very helpful. And on that note of shout outs to helpful tools, citations, etc., Tom asked in the chat about compiling that. Yes, we will do so, and we will put it up as a page on our workshop website. And when we send out the workshop follow-up email, we will include links to all of those. And we'll get back to the speakers to the extent you're able to share your slides with us. We would be happy to make those available on the workshop website as well. So Azalea, I was curious if you wanted to react to one part of what Mehek said, which is the tension between creativity and determinism. It seems like that's where verifiers can potentially be very useful. So do you see it as having this, kind of broad impact of being able to reduce this tension, or is the impact of verifiers limited to certain domains where you're able to easily build?
I think the verifiers and models, like generators and verifiers, kind of like their capability to some extent go hand in hand. Because if you're imagining the models, the agents are going to solve way more complex problems than they currently can do, and also compared to human experts, then in order to verify what these agents do, the agents need to have the same sort of capabilities, and their capabilities need to evolve with the agents as well. So verifiers and agents need to go hand in hand, become more and more complex, comprehensive, and I think that's the way to go for many applications, including the planning tasks, reasoning tasks, and conversational tasks. And there's always this question of like whether we want the models to be inherently correct and like verifiable, or we want to put in this external kind of agent that takes care of verification. I think I think both are needed, just like when we have for other domains like chip design, chip verification, we have techniques we have compilers, we rely on these synthesizers to do very well, but also we put these external verifiers because the consequences would be very high if we design a chip incorrectly. So same is true for LLM and agents. For different applications, depending on how much the verification and robustness and safety matters, we can put more and more effort in terms of compute and resources onto these verifiers. So we have this kind of external guardrails kind of ways to make sure that our agents are doing robust. And again, a lot of techniques, the techniques that we are using for each one, the agents versus verifiers, I feel like they're going to converge. They're going to be very, very similar down the road.
Interesting. Thank you for that perspective. Turning to Yason, there are a couple of questions about regulations. Broadly, what is the role for regulation, but also more specifically, given that AI developers might really care about the interests of the user, but less about the negative externalities to society, is there a particular role of regulation there? And let me also throw in one more question, which is more of a comment, less of a question, but I would still love to hear your thoughts on it, which is that most of the questions you listed on your last slide are an entire field of research. And some of these are really profound questions. So I guess I would be curious to hear your thoughts on how feasible this is as a researcher.
Yeah, thanks, Arvind. So maybe I'll take them in reverse order. The fact that these are already touching upon very well developed and rich fields, I think suggests that this is the kind of research agenda that we need. It would be more worrying if we were encountering kind of blind spots that were of such a great magnitude that there was not even a research field that had yet formed to investigate the harm in question. But fortunately, we do have resources and theories and bodies of knowledge that we can tap to build better agents, ideally before they even enter the world. With regards to kind of externalities and alignment and how how agents coordinate effectively at scale, it's really hard to come up with a generic answer without thinking about the specific kind of risk that's being created, whether it's misinformation or miscoordination. But one thing that my friend and colleague Gillian Hadfield has said many times is that artificial agents do tend to be regulated. It's not the case that corporations or other kind of fictive agents just have free reign to do whatever they want. Agents need to be kind of governed, they need to be identified, they needed to be situated in terms of frameworks which make their kind of actions legible, create some opportunities, and potentially cut off other affordances. So I think if we really do create these kind of very ambitious and capable agents, the question of how they enter society is a kind of one that necessarily taps all these interfaces. What kind of norms are appropriate, what kind of governance structures, and what else beyond that.
That's wonderful. I think we have a few minutes left, but I'm going to thank our speakers now so that we can have just a couple of minutes of closing remarks. Thank you so much. This has been so illuminating. I learned a lot, both from this panel and throughout the day. And like I was saying a minute ago, we're going to follow up with a lot of resources over email. And now I will turn it over to Zach and Nithya for a couple of reflections on the
So I'd like to thank you all for joining the workshop today. We're just going to take a few moments to share some closing remarks and ways you can get in touch after the event.
So yeah, we just wanted to share, the workshop has had really broad reach. We've had over 500 people in attendance, which is great, and from really throughout the whole world. So you can see on the map, truly global reach from over 70 countries. And many people are coming from, industry, which I think is, sort of shows the promise that people are seeing in agents. But at the same time, we have some university, many people from academia who are attending. So we're really happy to see that. And we'd also, as Benedict mentioned in the beginning, would love to stay in touch with all of you to hear more about sort of what are the ways in which we can build evaluation systems for agents that are practical for the use cases that people are using in industry. So we would love to stay in touch with you. And I think Nithya is going to also just talk a little bit about how you can.
Greatly appreciate any and all feedback that you have on today's event. You can do that through the feedback form that's linked on the screen. And you can also visit the second link on the screen, which is the same as the YouTube live stream link, to watch a recording of the panels and the event after the event is over. And lastly, thank you again for joining, to all the participants and panelists for sharing your insights. And we hope to see you again at future events.
Thank you again, everyone. This was such a productive session. Take care. Bye.